trends of the science. Maybe you have heard about the open science or citizen science or anything. And that is no longer the only pure, say, selected, elite, I'm not sure whether they are clever. The scientists are privileged to do the science by their own word. It is no longer the current science is no more one-man show. Almost any good achievements are conveyed by big projects of thousands or millions, thousands of scientists. So think about the gravitational wave measurement. It is almost one single big team. Big teams are covering the whole world. And this tendency is getting more and more. And soon, I suppose that the number of the elite scientists are not enough to promote the science to the next stage of level. We do need the efforts by the ordinary people. But now the flourishment of the culture and say living level and the many, and especially in Japan, many retired people have nothing to do. I hear many people, aged people, they are so talented and they covering of various fields, industrial, the commercial, and many things, not only the pure scientific people, but they do still had the intention to participate in science. And this workshop conveyed the very good facility or device to send them the current scientist size message through the real facts. This is quite important. After development of the computer and the graphic simulations, many people are aware that most of the current entertainment, say movie or 3D movies or something, are almost fake. Even some president says that CNN has made some kind of. I suppose his words have some kind of objectives. Even CNN may not be so wise as far as the science, scientific result, because the science is so complicated that it is quite difficult to understand the current cutting-edge science content and background and this correctness. I don't want to cite bad reputation of the Japanese science. Have you ever heard of the STAPS? So, it not only itself, but the other similar fake science facts. That kind of spread is quite dangerous for the sound, clear, and good advertisement of the ordinary, very honest scientists. For that purpose, we do need the support by the facts, not guess or idea or imagination. Sometimes it's good, but the final decision making is as further for the natural science. The God make decision. God name the nature. Even if a very smart theory, if this prediction is betrayed by real facts, then it has nothing. So the quite important point is the connection between the facts and the good or new style of the, say, message sending. So this data to dome workshop represents that very well. So quite important is the, say, selection of the good quality certified data, and say after say making because the data themselves are quite difficult to understand and not entertaining at all. Just the digits, or just the graphs, and most humanity people cannot understand or never wanted to understand or appreciate the number of these numbers, graphs, or formulas, math, but they can or they won't entertain, say, view, image, sounds, and sometimes very good talks about the talented people. So that this workshop, I suppose, that there is very good forum to connect these facts, scientifically correct facts, and the good entertainment as the domes. So I really hope that through this dome D2D workshop, you will advance this quite good, new, and promising the facility to get to the next higher level. Thank you very much.
Thank you so much, Fukushima-san. A very impressive talk. And next, I also look at the opening address from Mark Sublaro, the Adler Planetarium in Chicago. He is also IPS President-elect. Mark, please.
Good morning. I need to. Thank you very much, Ito-san. Well, I really want to thank you all for coming out today. And I know it's been a long way for some of you, and it's great to see a good turnout. The reason we're here, I think was summed up very nicely in the opening talk. We're entering a future, as many of you know, where more and more data is becoming available. And at the same time, our hope, and our firm belief, is that by sharing that with the public as quickly as possible, we can create a greater understanding. We can elevate the public's understanding of science. So this is our problem. We are, hold on. Here we are. And if you look, do you see the data written in there? The giant wave with the data? The data is coming to get us, right? Unless we're prepared. And so this whole idea of data to dome is that it's not just, if we're going to be ready for big data, we have to be ready for small data first. So we have to understand how to be smart dealing with data. This idea here, data to dome, comes from this idea from, well, I like to eat, farm to table, which is an idea in the culinary world that if you can reduce the amount of steps that food takes from going from a farm to winding up on your table, if you can make that path as short as possible, the food will taste better, it'll be better for you, it'll be cheaper. The same thing is true of data. If we can reduce the number of steps that are taken from the time a scientist makes the measurement till we visualize it in our domes, it'll make it easier for us, and we can do more. We can show more science. We can show more modern science. So part of this philosophy, so data to dome was really a philosophy rather than any particular standard or technique. This philosophy means that as a planetarium or science visualizer, we want to work more like a scientist, right? So we want to bring the outreach world and the scientists together. So we're working in similar ways. And that's what I'm going to show you some examples of this morning. There are going to be four workshops this morning, and then in the afternoon we are going to have a practicum where we can practice some of the things that were shown in these workshops. And one thing as we go through these workshops, I'd like each of you to think about what you want to do during that practicum. We're going to actually ask you to divide into 4 groups with each of the 4 workshop organizers, and we'll lead you in different projects related to our workshop. So think about that as we're going through this material now. For my content, I have a website here for actually all the content that you might want to type in, and if you haven't, you can see over here. Here's the how you can get on the Wi-Fi, and that has some of the instructions. So I'm going to get out of this presentation now. So if you were to go to the GitHub page, you would see this. We have this is a page from the International Planetarium Society's Visualization Task Force. We have a workshop page, and to make it simple for you, I've taken off everything except for this workshop. I've removed all the old workshops, so it's not confusing. There are a couple ways that you can proceed. So if you installed all the software that was sent out and you have that working on your machine, and hopefully you've downloaded, you can clone or download, and that either one is okay. That'll allow you to run the software. We'll copy the software on your system. If you choose clone, that means that if you make changes, you can actually submit them back to me, and we can update the instructions. Now, if you didn't get all that software working, I have 2 more options for you. So in my workshop, I'm going to go through 3 tutorials. You can either, if you just click on the tutorial, you can see the results. So for example, I'm going to pick one of them. If I just click on one of them, it'll open up a page and it will render the code as HTML. So you can read through. So that's one option. But another option, again, if you don't have the software installed yourself, I've installed it on a server in Chicago, and you can run that remotely. I don't know if this will work for everybody. We've not tested it with many people running it, but we'll see how well it works. But if you click on this button right here, that'll take you to this page. And then I can open up the notebook, and it's now starting this server in Chicago. And now we're connecting to the server in Chicago. And I can run the code there, even if you've installed nothing. But, however, I have it installed on my local machine, so I'm going to run it right here. And to do that, I will open up the command prompt, and I will type Jupyter Notebook. It's starting up. Okay, and I will look in the workshops and the data for this workshop. And now we'll step through these workshops. So what we're looking at here is something called a Jupyter Notebook. I will start with this one called Visualizing Gamma. And this environment of using the notebooks, using Python as a programming language, and using all of the astronomical libraries that come with Python is really a new way to do science, a very powerful way. So if you're a little bit older, like me, we learned to do this the hard way. It's much easier now. So I'm going to try to just show you very quickly. We'll have more time if you want to go in detail, but what I want to show you is why this is a really nice environment for doing science, for doing outreach, also for collaborating. And the reason is that it's not really that you have to program. You can really think more like a scientist than a programmer, and I'll show you that. So the nice thing about sharing these is I can have lots of words, so there's some stuff to describe things here. One of the projects at the end, one thing I would love to do is get a translation of this in Japanese as well. So perhaps during the practicum, one project could be translating some of the text for the workshop into Japanese, and then we could keep that on the website forever, and other languages as well. All right, so this is really, this way of working is becoming very popular among astronomers. What we're going to do is look at how I would visualize an astronomical catalog in many of the different space engine software that are out there, the different programs that are driving planetaria around the world. And so I've chosen a database. I've chosen a galaxy survey called Gamma, an Australian galaxy survey. And the reason I chose that is it's very interesting in that they've measured many, many parameters about each galaxy. And that will give us a lot of data to do different visualizations about. There are different ways to get that data, but they have a database, and you can query that database to pull back the information you want. Let's see. So for example, here is their website, and they have different tables of information and lots of different quantities. And you can request that in a SQL query. So you can do that on their website, and you can get a file, and you can load in that file. However, one really nice thing that we can do, and what I'm doing here, I've got two versions of this. What we're going to do here is actually, hold on, I'm going to restart this. So let's restart this and clear the outputs. When you open these notebooks, you'll see that the results of the code are listed after the code, and I just erased them. So we'll start over from scratch. So I'm going to do that first block of code, and what that's going to do, it's going to load in some of these packages, AstroPy, which has astronomy packages, AstroQuery, which lets me query another database, and I'm going to send that query to a database. And I will get back, hopefully, the network is good, hopefully I will get back some data. Let's see. So if you look on the side next to the in, you see the little star? That means that this block of code is still running. It's now downloading this FITS file, and it's now done. Okay? Now if you are running these yourself, I have some code to write it to a file and to read it. It's included on your flash drive, just so we don't have 50 people downloading the same data. But we just got 50,000 galaxies from this server in Australia. And if you might have done it from my computer in Chicago. And another nice thing about this environment is I can have instructions, I can visualize the data, and I can manipulate it all in the same environment. So here I'm just going to take a look at some of this data. So I'm going to make a plot. I'm going to plot where it is on the sky, the RA and DEC, and I'm also going to plot the redshift distribution. So I run that, code is running. Oh, and look, there's a Facebook notification. And here are the results. So this is, the survey is in 3 little patches that are on the celestial equator. And there's the redshift distribution. So it sort of peaks at about 0.2, it goes out to 0.4. There's a little peak there at 0. Those are probably stars, probably a mistake. So that's really nice. So let's look at what I have in this table, okay? So if I just say galaxy table, so that's the name of the table I downloaded. If I went back up here, I grabbed this and I called it a table. One of the nice things is instead of dealing with sort of abstract data structures, I can deal with astronomical quantities. So when you program like this, you're really thinking like an astronomer. So my table is really a standard astronomical table. So I'm going to add a block of code here, insert cell below, and I'm just going to say, what is my galaxy table? And I'll run that, and I can see the table. So it's 53,000 objects. It shows me the beginning and the end because you don't want to print 53,000 things in your browser. And you see all this nice stuff that I've got here. So metallicity, the age of the galaxy, its mass to light ratio. So let's do a few more things. So I have a redshift, but I want a distance. So I have to do a calculation to get the distance, right? So one of the really nice things is that AstroPy also comes with a cosmology package that understands some of the latest results. So for example, in the past, often when we make a dome visualization, we have redshifts for galaxies, and we need to determine a distance. The distance depends on the cosmological parameters. Every time there's a new paper by Planck, there are new cosmological parameters, but we never change the distances. In fact, often we don't really even know how we got those distances. Now it's actually very easy to do this, and it's very easy to make these calculations. So I don't know if anybody has written the code to do that yourself, but it's actually a lot of work. But here, I can just say, I'm going to get the Planck 15, so the cosmology from the Planck team's 2015 paper, and I'm going to use that cosmology to calculate both the co-moving distance of the universe at a redshift of 0.4 and the age at that redshift. And I do that. So it tells me what that cosmology is, right? These are the values of that cosmology that were in that paper. And you see I'm dealing with scientific quantities here. I'm not just dealing with numbers. So I have an age in gigayears, about 9.3 gigayears, and I have a distance in megaparsecs, about 1600. There are lots of things that I can do. So if I, for instance, type this, blank 15, dot, and I hit tab, it'll show me all the things that I can measure. So now, especially if you did astronomy a few decades ago and you remember how hard it was to calculate all these things, you can be jealous for astronomers who are just starting now, because you can get all of these quantities calculated very easily. All right, and so for the distance, I want to, often there's some debate about if we're plotting things, visualizing a extragalactic data set, what distance to use. There, as you may know, there are lots of different ways to measure distance in cosmology. I recommend using the co-moving distance. So that's the distance. If we could stop the universe from expanding right now and go out and measure where things are, that's the distance that we would use. So I recommend plotting things with co-moving distance. So I'm going to now calculate the co-moving distance for all 53,000 galaxies. And it's done. If I plot that table now, you'll see I have a new column called co-moving distance, and its units are megaparsecs. Okay, so before we get this in a planetarium system, there's one thing that's a little bit complicated. There's this one number or one column I pulled back called EM line class. That means emission line. So it's classifying galaxies as either a star-forming galaxy or a regular galaxy, but it's not a number. And the fact that it's not a number makes it difficult for our software to deal with. So right now, I'm going to check. So if I do this, this will tell me what are all the names. And there are three different names: HEN, SF for star-forming galaxy, and XXX for it's not either of those. And what I'll do is I'll replace those names with numbers with this piece of code. Another really nice feature with AstroPy is I had that ability to print a table, but if I want to look at the entire table, I can do that as well by this command below, which is show the table in the browser. So if I run that, I get the full table. It's still loading in. So if I go down here, I've got different pages, and I can search for a name. I can also sort by clicking on things. So the highest redshift galaxy is 0.59. So another just example of how nice this environment is to work in. All right, so let's look at how to put this table of data into some of the different software packages. So first, let me start up. Next, Doug Roberts will be talking about Worldwide Telescope. So I'm going to start Worldwide Telescope running. I think it's running. All right, let's wait for it to come up. And I really strongly recommend, if you haven't tried using Worldwide Telescope, you'll see why in the next presentation, but it's a very powerful tool, regardless of which planetarium software you're running. So there's Worldwide Telescope. It has a 3D view and a sky view. So what I'm going to do is I'm actually going to connect to Worldwide Telescope with this code. And this is using this package that we asked you to download called PyWWT. I'm going to connect to that instance of Worldwide Telescope. And I am going to connect to it running on my own machine, but I don't have to. If I put in an IP address here, I could connect to Worldwide Telescope running on a different machine. In fact, if Worldwide Telescope was running in my dome, I could be sitting on my laptop running this notebook and sending data to the planetarium dome directly. Not only that, I could have a class with 15 students, each with their Jupyter notebook, each sending different data sets up to the dome. So let's show you how that works. So I'm going to connect to this. And it connected. And then I'm going to create a new layer, which I call Gamma Galaxies. And I'm going to set up some visualization parameters. And then I'm going to send that to Worldwide Telescope. So let's run that. It's done. Let's go look at Worldwide Telescope. Let's see what we have here. So if I look in 3D view, I see Gamma Galaxies. Let me zoom out of our galaxy. And look, so that's the Sloan Digital Sky Survey, but these three bands over here is the Gamma Survey. And in fact, it's in the right place, right on the celestial equator. All right. I can switch to sky view. And I see them there. I can change how they're visualized. So in sky view, that's not such a good way. So I'm going to right click on this. Make them all circles, and let me make them a little bigger. So I'll see circles, and these should be circles where galaxies are. And do you see any galaxies where the circles are? Maybe not, but I think it's just because our imaging isn't deep enough. I'm going to switch to the Sloan Digital Sky Survey. So now I'm going to load in a different image background, a deeper digital imaging. And now you're going to see, as the data comes in, little galaxies where each of those circles are. So that's a really nice interface, being able to directly connect to the data that way. But there are other ways, and I'll just show you for some of the different systems. So does anybody have an ENS Digistar system? I think two people. So there are a couple of different ways to do that. But starting with Digistar 5, you can upload a virtual observatory table file. Which is a really great thing. Unfortunately, in their documentation, they don't tell you that that's what you're uploading. So it's a kind of secret feature. And that table has to have certain columns for it to understand. In fact, the first three columns have to be Cartesian coordinates of distance. And then the other columns can be anything you want. So what you'll see here is the code to make those first three columns that Digistar demands, and then to write it out as a file. And you'll see it's called a .du file because they call them digital universe files, because that's how they store the digital universe data. But in reality, it's a virtual observatory table, standard astronomical format. One of the nice things about this format is that it has these parameters called UCDs, which describe what each column is. So that the software, if it's smart enough, can read that column and know exactly what each quantity is. So it can know which quantity is a distance, which one's a brightness, and automatically figure out how to visualize it. Okay, Digistar users. Do I have some Digistar users or SKISH users? Yeah, so many more. In this case, there are some different options, but the standard way to put in a catalog of data is in party view format. Party view is just an ASCII table, and that ASCII table again has 3 columns that are Cartesian coordinates, and then extra columns that can be other quantities that we want to visualize, like in this case the metallicity or the age of the galaxy. And in general, there's a difference in that usually in these systems it's in galactic coordinates. So this code will add, delete those 3 columns from the other table, and it will now actually convert from the standard projection of equatorial coordinates, right, ascension, declination. It'll transform to the galactic frame and output Cartesian coordinates in megaparsec. So you don't have to understand this now. The point is that you can copy this and use this on different catalogs. So the spec file, which is used by party view, also has a header, and this describes what that header looks like. That tells you what each column is. So we're going to write that out, and then we just write the file, and we can read that in. Anybody use RSA Cosmos, Sky Explorer? Nobody. If you did, that file is written out in a different format, something called Open Scene Graph, but with a little extra text, we can write that as well. Now, of course, this will give you the data to make a bunch of points in space, and that's one of the ways we've been looking at in the planetarium field galaxies. But it's more interesting to try to look at some of these other parameters that we've pulled out. So here I've got some code that can help figure out if we want to, say, color a galaxy by different distributions. So if we look at the first piece of code, we're going to look at the star formation rate of galaxies. So I'm going to run this. And this will make an image. And this is an image we'll save to file. We could actually take this image and load it into the dome. But we will have a mapping of star formation rate to color. And we need to get that color into our system. If you use, again, the UniView system or the digital sky system, that file, the party view file style, is called a CMAP file. And this code will generate a CMAP file that corresponds to this color map. And this is a very nice color map. So, and I run it there, and I've just written that to disk. And I can use that when I'm loading in the data. All right, so I'd like to quickly just show you some of the other 2 tutorials. Again, I'm not expecting you to completely follow along here, but what I want to do is give you an idea of how things work and also some idea of what we can do later on in the practicum. So for example, this code could be used to connect to other databases. In fact, there are about 15,000 astronomical catalogs you can access automatically in this way, almost every catalog that's been published. And we can put it in all of the planetarium systems just by following these instructions. So we suddenly go from having almost an unlimited selection of data. Let me quickly show you another example. So this is an example trying to show, I think one of the things that I'm most excited about in terms of capabilities that have been enabled recently is the use of user-programmed graphics shaders inside the Space Engine software. Right now, this capability is often hidden. People have been working on it and creating interesting things. It's certainly poorly documented, and some of that capability isn't as well exposed as it could be to really unleash the full power. But there's incredible potential there. So this is one area I think we'd really like to push development. I'm going to show you an example with UniView, which actually does the best job of all the major packages, as far as I know, of exposing these capabilities. And what this means is that instead of just being an application where you can do what the software allows you to do, the user can write these little programs without messing with the main program. Just write these little programs to create custom behaviors that are incredibly powerful and fast, because you're writing on the graphics card, so extremely fast. So I'm going to show you an example that I did for a gravitational wave lecture, basically a small conceptual animation. The way that this works is that in our case, there are 3 different kinds of shaders. There's a geometry shader. That'll take one piece of graphics geometry and turn it into another piece. There is a vertex shader that takes each of the little points in the geometry and can move them around. And there's what's called a fragment shader, which takes basically the color that is being sent to a pixel, and I can run a program on it and change that into another color based on information. And the way that I've done this animation is really to trick the computer. So it thinks that it's getting a file which is telling it geometry, but it's not geometry, it's just data. We're encoding the data as a bunch of little triangles, but it's not really triangles. And then we're going to use that data to draw whatever we want. So in this case, what I want to do, and this is an equirectangular image of this, I want to make a cylinder of points on a mesh that are being warped by a gravitational wave as it passes by. And to do that, I first have to draw points for all those meshes. So that's what this code here does. It just makes a simple ASCII format that UniView can read in that has 9 numbers. Those 9 numbers are, a triangle is 3 points. Each point needs 3 numbers, x, y, and z. So it's those 3 numbers. x1, y1, z1, x2, y2, z2, x3, y3, z3. And then I can operate on that. So I can actually operate that multiple times. So what I do here is I pass through that data 2 times. The first time, I make a little square at each point, and I make that square point towards the camera, and then I draw a fuzzy blob on it, and I color that blob based on how much the space is being distorted at that point. That's the first pass. Then the second pass I go through, and I draw these connecting lines. So for each point, it needs 2 lines to connect, and that makes a full mesh. And I'll just quickly show you how that's done. So let's take, for example, this first one will draw the square. The marker fragment draws on that square, and it gets a number. which I send to it, which is the marker type that I can change. And that marker type will tell it what I draw on there. So I can draw the fuzzy blob that I showed you in the picture. I can draw different things. So let's take an example of, let's see what that looks like. So I'm going to start Unity View. Not that one. D2D Tokyo. I'm going to start this up and we'll see what these shaders look like. So we don't really have enough time to go in this, but this is a simple example for you to look at and something for you to go back and explore in your systems. I think this is really where we, the users, start to take control of this software and make it our own. Almost there. And I have some shortcuts here. So let me go here to my shortcut. And this is what we've created, this ring of particles that's being distorted over time. It's responding. The shaders know about this simulation time. So it's responding to that. So if I stop that, it will go. And really it's just getting a sine wave that's compressing and distorting the shape. But you remember I drew a whole cylinder, not just a ring. And that's because I had a parameter. I sent it a parameter which tells me how much of the cylinder to draw. So I can hit this grow button and I'll expand that number. And it will draw more. Fly into that. This is seriously trippy in the dome, by the way. It's pretty cool. You can see some of the other things. So I showed you that the code for the fragment shader, and I said that by default I'm drawing a fuzzy blob, but if I send that a different number, it will draw different things. So if I send it the number 1, it'll draw these things. I set it to number 2, it draws that. 3, 4. Right. So basically, you have complete control to do whatever you want. And in fact, you can do pretty advanced things in here. Let me show you another example. So in this morning's address, we heard a little bit about our new president in the United States. Our new president has inspired me to start working on some climate change visualizations. So here's one of those. So this is made in a similar way, but a little bit more complex. We have a beam of radiation coming in. This is showing the Earth's energy budget. Radiation comes in from the Earth. Some of it's reflected, and then it heats up the Earth, and then it radiates energy away in the infrared. So you're seeing those different components here. But this is all being calculated. So it's calculating how to reflect off the Earth. It's calculating what fraction should be reflected. So for example, I could have all of the radiation reflected. I could set that to be none. I could change how wide this beam is. So I can make a tight beam of radiation. Or I could set that to be really wide. All that's programmatic control that you're adding by using the graphics shaders. All right, that's one. In the final 8 minutes, I'm going to just show you what the last tutorial is. We don't have much time to go through that. That's this one here. and this is dealing with simulation data. So the first two tutorials were really how to use the real-time system, but there's still times when those data sets can be too big to deal with in a real-time system. In that case, we do need to pre-render data sets. So this one shows you a really nice way to render using a package called YT, and this is a software package that's meant for simulation data. It can deal with many different types of simulation data. So often the challenges when dealing with this kind of data is being able to read it in and understand all the different formats. And this Python package, YT, understands most of the major formats. So we're going to try some volume rendering. And if you want to learn more, here's actually how you install it, Ryan. And here's some more instructions. And what I did is I downloaded, they have a bunch of sample data sets on their website, but you can go to that and get more. I just downloaded one snapshot of a cosmological simulation, a very small one, so it's not a lot of data. So we can just load it as simple as this. You can see what parameters are there, so all these things are measured, all these different quantities. And we can make some plots. So I'm going to make a plot of both the density and the dark matter density. And this is a slice plot, so it just goes through in one dimension and takes a slice through this cube. So this is a cube of data. I'm slicing through it, and the first one is the dark matter density, and the second one is the gas density. And if you look carefully, you'll see there's some big squares and some smaller squares, and this kind of data set is it's what's called an adaptive mesh refinement data. So you break that cube up into smaller cubes, and in places where there's more data, you break it up into smaller and smaller cubes. And that's part of what makes visualizing this kind of data really hard. But it's also one of the reasons why using something like YT is very nice. So I can pick, let me just try to visualize something with the density. I'll do that. I'll create a scene, and I'll look at that scene, and it's running now, and it's now doing a volume render. It's taking this simulation, it's tracing lines through, and it's measuring the amount of density, and it created this image, which is a little dim, but if you show it with this sigma clipping, it'll brighten up the image. And in fact, if we look at it, you can kind of see, you can see the cube, right? That's the edge of the simulation. And if I look here, if I look here, this will tell me about my camera. So I'm focusing at 0.5, 0.5, 0.5, the center of the cube, and my camera is at the very corner of the cube. So that makes sense when you look at this. I'm sitting at a corner of this cube looking at the center. And the type of lens is a plane parallel lens, so it's an orthographic camera. So Ryan, how do you feel about this kind of visualization? He is not a fan of this kind of visualization. And it's these fuzzy iso contours are very hard for the public to understand, but we have full control over how this is being done. So right now, this is just the default rendering, but I can look, there's something called a transfer function, and that describes how I go from measuring that density along the line of sight to making a color in my image. And I can do that according to any way I want. So right now, this transfer function, if we look at it, is a bunch of Gaussians, and each one of those is an isocontour, each with its own color. But All right, so when we can look at it, if we were to plot it, this is what it looks like. So the density has some distribution like that, and then each one of these little narrow contours. But we can make our own. So here's one that I made. Whoops, I have to go back here. I didn't run this code. Whoops, sorry. I have to go back here and do this first. And now I've made my own transfer function where I'm using actually the same color map that that I was using for the star formation rate. So this is a perceptually uniform color map. So as it moves along, things seem brighter and brighter. You've probably seen a lot of these sort of jet rainbow color maps. They're actually very misleading. But this is designed so that things that are brighter look brighter to your eye. They look more intense. And then, but I really wanted to focus on the cores of these, the clusters and the cores of the simulation. So I added a little bump just to accentuate that at the end. So let's do a rendering of that, see what it looks like. I'll save time, I already did the rendering. It looks like this, right? So now we're seeing the structure of the cosmic web, and we're seeing the galaxy clusters highlighted in yellow. And I can also render that out as a fisheye render, like this. So all I have to do is set the camera to type fisheye. I change the position, so this is the camera, and when I render that, I get a nice fisheye image. So that's just a quick tutorial about how to use YT in volume rendering. If you were to say wanted to make a movie of this, you can just move the camera slowly through this volume and render a sequence of images, and then we could encode that for the Dome Theater later. If you wanted to grab some more snapshots, I think they have about 40 for this simulation, but they have some other simulations. You could also step through those simulations and just do the same thing on a loop, and you could make a movie of this simulation evolving over time. So that's basically how that is done. So just to, we go back. Let's see, where am I? These are these 3 tutorials. Hopefully I demonstrated some different ways of dealing with different kinds of data, and also hopefully get you thinking about different things that you might want to try later. So this is all on this website, and you can use this code as an example. So even if you don't know Python and you're just learning, copy and paste is your friend. So there are enough examples here. Change a few numbers, run the code, see what happens, and very quickly you can figure it out. This is much faster than actually trying to learn this from the beginning. Start by playing with the examples and explore. So thank you very much. This is the end of my time. I'm also the chairperson for the session, so I will not allow myself to go over. I'll take a few questions, and then we'll have a short little break. Does anybody? No? All right. So Ito-san, did you want to say something about? I'm finished.
We have some information to participant about lunch. Sorry. We have a very busy program, so we have not so enough time. When morning session completed, you may go to restaurant Cosmos Lodge. It will be crowded during 11. Yeah, so you may hurry up to go to restaurant. I prefer it. Yeah. And other information, Makiko-san, okay? And how about Satomi-san? Okay. Takahe-san.
Hi. About workshop about open space. In your USB stick, there is a archived version of open space file, but unfortunately, it's too big. So in some environment, it's difficult to unzip the file. So I have the extracted file in a USB stick. So if you have any troubles for unzip the files, please use this one to copy the unzipped version. And also, in some environment, the open space failed to run. So I prepared the updates for that binary. So I think Satomi-san uploaded the file to the update data. Do you think? Yeah. How can I show that? So at least here is 6 USB stick files. So I will share this one. So in the next workshop's time, please copy the whole files into your laptop or computers. And if you succeed to extract the files from your USB stick, there is a small size update file to run the open space successfully. If you have any questions, please ask me in your break time. Okay.
Thank you. And also I have to introduce about organizers and cooperators and host, co-host, sponsors, but I will introduce at the banquet time, okay? And morning session, Mark-san will take chair in the morning session. Workshop 2 start 10:25 by dogs. We prepared, coffee and some drinks and cookies. The table. You may take any time. Now we take break.
So here you can download the update file of OpenSpace. So if you succeed to extract the zip file, please download the small update files. If you have problems about extracting the zip file, please use this USB stick file. Thank you.
Hello? Excuse me. So we're going to take advantage of the fact that I finished a little early and try to finish a little bit early so I have more time for lunch. But I have a request. Does anyone have a DisplayPort to HDMI dongle? Mini DisplayPort to HDMI. We do have this one. Yeah. That's VGA, yeah. Mini DisplayPort to HDMI. All right. Do you want to use mine?
Okay, we will start. Timetable changed 5 minutes earlier. We now start the next presenter.
So our second workshop will be Doug Roberts from the Fort Worth Museum of Science and History, is it? Science and History. And before that, Doug was working with the American Astronomical Society on Worldwide Telescope. So this is a project that started as a research project from Microsoft Research. It's now open source software. It runs in planetarium domes, and it's supported by the American Astronomical Society, who publishes the Astrophysical Journal and the Astronomical Journal. So there's a deep connection as we're trying to get more and more researchers using this in their publications. The connection between research and outreach can be pretty powerful.
Thanks, Mark. So I'm going to start with a little background, as Mark did a good job of introducing about the history of Worldwide Telescope. Worldwide, because I think this connection to the research piece is really important. I think everybody has this on their stick. In case you haven't downloaded it, you can go to worldwidetelescope.org/download, or it's on the USB stick was provided. There's also a web client there that I'll be showing. But Worldwide Telescope, just to give a quick background, was started, the seed of it came out of the Sloan Digital Sky Survey and a workshop around the data for that survey that was happened in Chicago about in 2005. And at that workshop, several of us were there, and the idea of taking the images of the galaxies from Sloan context of the background, that people could see the background and the relationship between what they can see with their own eyes or what they might see in a planetarium, and see that the galaxies from Sloan in that was considered to be an interesting goal. And this is proposed by Alex Zalay and Jim Gray from Microsoft Research, and they were working on the survey together. And then fast forward a few years later, now Worldwide Telescope is a software system that provides this sort of capacity to put images in context and also other data sets in context that's now being used in museums all over the world. It's free software, which makes it very attractive for nonprofits. The planetarium, they have it on large display walls, as well as in the planetarium dome. And Mark produced a fantastic show called Cosmic Wonder in Worldwide Telescope that takes advantage of this image in context capacity. It also, Worldwide Telescope as a project has an interesting history where they actually put together inexpensive instructions about how to make a cardboard dome, so you can make an entire planetarium dome for around $1,000 US. And so the instructions on how to do this was put on a website, and I know of at least a couple that just out of the people who did this without even asking the Worldwide Telescope team, they just went to the website, bought the cardboard and the paper clip or the binder clips and made their own dome. The only problem is some places, one place I know tried to build this, and the fire marshal came in and said you have to have a sprinkler inside this cardboard box, which is kind of crazy, so be careful about that. So, as Mark mentioned, one of the powers of Worldwide Telescope is it is a piece of technology that's fairly easy to use. I'll show you a little bit in a second. And it really, hopefully, if you're a researcher, you can use it in various ways. You can use it to, in your teaching, in your undergraduate and graduate teaching. You can do it in community outreach, in using Worldwide Telescope to create videos or taking out to the public. You can do your own data exploration. What Mark was showing with the Python notebooks is an example of being able to load and interact with data. You can also do data contextualization. So if you have your, in astronomy, it's very common, of course, to have your field of study that's very narrow. You know it, and a small group of people also know that one thing. For instance, I'm a researcher who researches a black hole at the center of the galaxy, Sagittarius A star, and there's a few hundred people in the world that really focus on that. But then if I want to share that with my colleagues outside of that very narrow group, Worldwide Telescope provides a way to contextualize the galactic center with everything else. It can be used to do student projects, and then more and more, and this is kind of the interest of the American Astronomical Society, is this idea of data sharing and data behind journal articles and scholarly publishing. The timeline for Worldwide Telescope is interesting because, as we mentioned, the impetus came in 2005. The first release was in 2008, and then a few years later, they came out with a very powerful 3D solar system mode, and you'll see that. I'll give you a demonstration of that. But it represents the planets in our solar system. It has high resolution terrain and height map data as well as image data on top of the different planetary bodies and minor bodies, and so that really enabled a full planetarium-like system to be put together with a free software system like Worldwide Telescope. Shortly after that, Microsoft Research created this full 3D mode. They decided to turn it into an open source project. So now then they took about 6 months to transfer it into GitHub, and so you can go to GitHub and get the source code, and like as Mark mentioned, with the way GitHub works, you can clone it, and then if you wanted to do work on the source code in any manner, you could make the changes and then submit pull requests to merge it into the mainline code tree. The copyright of Worldwide Telescope is managed by this organization, not-for-profit, called the .NET Foundation. So Worldwide Telescope is primarily written in .NET and C#, and so that foundation is meant to support those sort of open source projects. And then the American Astronomical Society decided in January of 2016 to take on Worldwide Telescope as a project, and so they're supporting the continued development of it. When I was with the World AAS, I wrote a grant to the National Science Foundation, which is going to fund that for a couple more years. So I think there's great interest in the astronomical community to use Worldwide Telescope and to support it. The thing that excites me as a researcher and an educator about Worldwide Telescope is really this ecosystem that it provides. It's a tool that can be used in all these different ways. So when I create if I taught a college class on the solar system, every talk that I gave, I would give an overview in Worldwide Telescope of the areas that I was going to visit, and then I would go in and then I would talk more about, like if I were talking about Mars, I would give a flight over the major features that you could see from orbit, and I would kind of script that, and then after I kind of gave that introduction, I would then go in more detail about looking at Olympus Mons and Valles Marineris and Dust Devils and all the different components of Mars once I've given this kind of global overview of where things are. But then I can also take the same data set, and I can use it for outreach, to take on star parties and put in planetarium domes. If it's my own data that I'm using, I can use it for professional talks. And as I mentioned before, research and publications are kind of interest of the American Astronomical Society, because they want to create a tool that can allow for scientists across different areas of astronomy to talk to each other and intercompare data sets. So I'm going to stop the PowerPoint and actually just kind of show you Worldwide Telescope as a package, just kind of show you some of what it can do. So I'm going to use a mouse here and try to do everything. So Worldwide Telescope has this these different modes, and so the first mode that I mentioned, kind of motivated by the Sloan survey, was the sky mode. And so this is a mode. Now, right now I have all the constellation lines turned on. I'm actually going to move over here so I can see what I'm doing. So, oh, I may be too far away from my mouse, so I'll go over here. So if I go over to, actually, if I see if I can get over here. Okay, this is going to work. Okay. So if I turn off constellations, now I have just kind of the blank sky. I have different data sets that I can do in all sky surveys. So I can either in the sky mode pull down and look at like a Planck CMB background. I can look at Glimpse 360. This is a galactic plane survey from Spitzer. It covers a few degrees of latitude and the whole 360 in longitude. I can look at hydrogen alpha, all sky. And so these are all single maps. I can also go up here and I can click on all sky survey, and the same image, same surveys that are here are available up here. But if I want to say compare this dust, I can say set that as background, and then I can say set Y's as foreground, and then I can crossfade between them to show how they compare between two different all sky survey wavelength bands. So this is a very powerful way to introduce the topic of multi-wavelength astronomy. Also, you can choose whatever background image you want. So again, this idea of context, these don't have to necessarily be one all sky compared to another all sky. They can also be images. And when I'm looking at the viewport here, everything in this bottom menu is a list of things that are visible within that frame. So when I roll over my mouse over these objects, you can see a little circle pops up where it is. If this thing in the bottom has a little icon that says a picture in the upper right, it means when I click on it, it will go. I can actually see that picture overlaid. Now, right now, I'm overlaying this high resolution image on top of this H alpha all sky, and if I pull back, you can see there's just a burned out version of it. So I probably want to choose a different all sky background. So I mean, it's higher resolution. So I'll go back to the optical digital sky survey, and now when I zoom in, I see this high resolution HST image on top of the lower resolution all sky survey. So you can. I'll show you in a second how to script this, or what we call create a tour, and it allows it's the sort of thing you would do for a public experience or even for a professional presentation. If I'm giving a talk to my colleagues, I would want to script what the data sets that I'm showing and so forth. So when I pull out, you'll see that more things will populate along the bottom because now my field of view incorporates more objects. Again, I can go to this globular cluster, zoom in, and again compare this burned out low resolution to this higher resolution image, color image of the same object. So this is a sky mode, and again, you can intercompare various data sets. Worldwide Telescope has a large number of data sets already in the system. of various background and foreground and these pointed observations, but you can also include your own, and I'll show you that in a second. So that's one mode. The other mode I mentioned that happened a few years ago is this idea of a 3D solar system, and this is more like what you would see in a planetarium. So I think I have to turn on planets, planetary orbits. Let's see, what is... Okay, well, I guess I didn't have the Milky Way or the stars on, so that's why the universe was empty outside the solar system. Okay, so the solar system, is here. We can go to our favorite planet, the Earth. And one of the cool things you can do is, this is kind of fun, is you can do a search on different cities. This is just totally for fun, but I love doing it. So let's look at Seattle. And this again, did I? Oh, Settle, and Settle is probably not going to be a named a 3D city. Seattle, is that right? Okay. So let me click on this, and now I'm in shadow, so I can do one, two. Right now, I'm just going to turn off lighting. And I'll zoom into Seattle. Oh, I also have to stop time because the Earth is rotating underneath me, so let me pause time. So as I zoom in, these data are actually from Bing Maps, and now let me kind of rotate it so you can see the cities as three-dimensional objects. So one of the cool things you can do is, again, if you're trying to make a story where you want to connect people with where they are, either maybe connecting a location where you're giving a talk, or where people might be directed to go to see an eclipse, or you can actually put 3D models like an observatory in these systems. Another cool thing you can do is I can put myself at a location of a street corner and set the time to say when, like, what would I see if I looked up, like, when would Venus cross between those two buildings? I could actually get all the timing and so forth correct to talk about that kind of alignment, where I'd have to be to see things and stuff like that. So the 3D cities is just kind of a fun extra data set that's there for free. But then on other planets, if I fly to Mars, similar high-quality data sets. Again, it all depends on the data under the hood. Worldwide Telescope has a fair amount, a very large, about 15 terabytes of data internal to Worldwide Telescope. And actually, the high-rise image set from which I don't have shown here, they would be shown as strips in the way that we render it right now, is itself about another 15 gigabytes of terabytes of data, rather. So the data sets can be quite large. The way Worldwide Telescope works, all the data is served in the cloud, and then the client just pulls down the data that needs to render the scene that you're showing. So it's a combination of where I'm looking, how many what kind of data I need to represent the direction I'm looking and the detail I'm at. So it's very efficient. It's kind of all designed for network transfer of data sets. All the tiles that are used to compose these images are stored in a cache, so that if you've gone to them once, you don't have to go to them a second time. So that's one way that we can use it for offline, or if you're going to take this into a school, you can do that sort of thing. Again, you're kind of the data in Worldwide Telescope is quite significant for most of the solar system. I can pull back show the orbits of the planets. I could turn on, and most planetarium software has this capability of turning on like asteroids, and then turning on time. Oh, now see, I'm tracking Mars. So actually, the frame of reference is Mars. You're seeing everything kind of nodding around Mars, but that's I should have tracked the sun for this kind of visualization. There's two other modes that are kind of cool. One is called panorama mode. So this allows you to look at high-resolution panoramas from various missions. So this is a spherical panorama. And one of the cool things I love doing personally is, I saw Patrick has one, but I know people here have seen the Ricoh Theta cameras. It's a spherical camera. You can take a spherical camera and actually, if I had it connected to my computer, if I had a picture on my Ricoh Theta, I could just navigate to that file and pull it into Worldwide Telescope. So actually, I think, let me try that. That's actually a pretty cool thing to try. I don't have it connected, but I took some pictures. Actually, I'll do that later. It might be kind of fun for a practicum. If people want to do that for a practicum, that would be an interesting thing to try. And take some pictures of a location of an observatory, and then have a high-resolution picture to go to. Again, these are built in, but you can build your own. And again, the Ricoh Theta thing is easy. And there's a way within Worldwide Telescope, and I'll try to kind of touch on this near the end, of taking any data set. There are two ways to include data. If I were to pull in a panorama that I'd taken, it will be attached to the system as kind of an add-on file. But if I close it, if I try to send that to somebody else, it can be sent, but it's those sort of extra images get added to the file. Another way to do it is to process these images in a way that puts them into this format called Toast, which is the underlying tiled multi-resolution format that Worldwide Telescope uses. And they can be put on any server that you want, in the cloud, for instance. That's where all these data live. And then the tour that I send just has a reference to those data, so it doesn't actually have to transfer the data. So those tours can be quite small and very portable, because people anywhere in the world can see them without having to move around large data files. There's one more mode that's interesting, called the sandbox mode, and for that, just as an example, if I go to sandbox and add, I'm going to try to get a file. Actually, yeah. So actually, I haven't looked at this before, but so this doesn't have texture map on top of it, but you can load in three-dimensional objects, and we did this if you wanted to go outside astronomy. I think one of the things that, we're obviously very interested in astronomical data to DOME, but one of the things I think that we should be thinking about or some of us would think about is are there ways to get other sorts of data sets into using the same workflow into the DOME? In the United States, and I'm not sure what it's like in Japan, but there are a lot of domes that are associated with universities, and those domes are not just servicing astronomy. Well, right now they do mostly undergraduate astronomy. That's one of their connections, but they want to be able to bring in chemistry models and three-dimensional models of medical imaging and other things like that, and there's at least a way to do that through this data set import. And if that's interesting, we can also look at that at the practicum. So those are the different modes of Worldwide Telescope in terms of the data sets. So the two things I'll kind of go next, and let me go back to the PowerPoint. Oh, by the way, there's a website. Let me kind of pull that up to show you. I think in the thing that Mark set up, he has the website for that has a link to this website. But I made a workshop website from Worldwide Telescope It's actually Worldwide Telescope, or WWT workshops. Actually, wait a minute. I can't spell. So this is our workshop here. And by the way, so if anybody wants to go to www.workshops.org and then click on our workshop on the left, then my talk is actually here as a PDF. And then if you want to follow along any of the catalog data, the resources that I'll be pointing out are all listed in basically in these parts here. So everything here is a link to different data sets. So I'll go back to the PowerPoint, but it's basically the same as the website if you ever want to follow along. So Worldwide Telescope has the ability to bring in VO tables of catalog data. I'll try to show that in a little bit. By the way, Mark, I should be ending up at 11:20 or so, or 11:15. Okay. So VO tables are this standard to give, again, the sort of idea of having data served by different repositories and then have references to the data in a standard format. Also orbital data from the Minor Planet Center. You can pull in orbital data of different objects. I'll show you how to do that in a second. And this idea of 3D models, like I showed you, pulling up the Chandra Observatory, a spacecraft, but obviously that didn't have texture maps, but you can make sure they do, and you can put them into in various ways. You can load a 3D model on an orbital path. So I know Carter's going to talk about open space, and that has a much more sophisticated way and much more accurate way to do that. But if you want a simple put a body on an orbit, or if you have a 3D model of an asteroid or something, a really high resolution model, and know the orbital parameters, you can create the reference frame for the orbit and then put the 3D model into it. And also this idea of observatories on the surface of the Earth is very powerful. You can make a 3D model of, pick your favorite observatory, find its location on the Earth and scale it properly, and then you can plop it down, and then it's embedded in the same environment as everything else. And then the sandbox mode is the last piece I was mentioning, where you have this ability to bring in 3D models of anything and put them into just a model viewing program outside of kind of the rest of the universe. I didn't mention this in a slide, but I'll just take a moment to mention that one powerful thing about Worldwide Telescope is that it runs, the desktop client runs on various types of machines and configurations. So it runs on obviously a laptop or a desktop and a single flat screen. It also runs in planetarium mode. Out of the box, it can drive a fisheye projector or a mirror dome system. And then if you have a multi-channel system, there's also a way to install that on that sort of system. So it's a very flexible package. And there is support for Oculus Rift for both the development kit versions and new support for the consumer version. So the nice thing, again, about Worldwide Telescope is that you can create a tour and then actually display it on a flat screen for a college class or a high school class. Or a professional audience, dome if you're in a dome, VR if you have access to the virtual reality machines, and so forth. So as far as getting data into Worldwide Telescope, that's obviously the kind of purpose of this workshop. There are various ways to do that, and there are different types of data. So one is image data, and I'll go into that. Mark mentioned this idea of connecting via the API to Worldwide Telescope. Connecting to it with something like IPython notebooks, so that you can be both sending data to it as well as telling the system how to render it and how to control it. WMS, Web Mapping Service data, is another way to get data sets that are pointed towards WMS maps, especially on the Earth. And there are some new, some planetary missions are trying to make WMS data available for other bodies. They're trying to make a standard for generic solar system bodies. All sky panoramas and surveys, so that the panorama that I showed you of Mars, or I mentioned that Rico Theta can take a full spherical image those can be tiled in a way, as I mentioned, and put into the cloud, and then you can reference them much faster, and it's much more higher performance for visualization. And panoramas and all-sky surveys are two ways to look at the same sort of data. And then there's a really powerful new, and this is the thing I'm actually most excited about, called Montage. It's out of IPAC at Caltech, and Montage is a system that you can basically either use a single image or multiple images it actually can do the combining of multiple images that go into a survey, and do that stitching and tiling into Toast for displaying Worldwide Telescope directly. So I think this might be a fantastic a practicum thing. If anybody had an all-sky survey they wanted to get into Worldwide Telescope, I've actually tried to. I meant to ask you, Mark, have you ever used the new Windows 10 Bash tools? So Windows, as people here know about Windows 10 now has the ability to have a Linux subsystem included into it, so it's a development kind of add-on, but it's a very powerful new system, and I'm going to try that out as a practicum if somebody wants to kind of help me with that, to use the montage tools in Windows and see if we can get that working. But Montage, again, has this ability to look at very large data sets of fits. It converts them into Toast has a very excellent color map algorithm to apply color to it, as well as tools for reprojection and image comparisons. So let me actually go back to Worldwide Telescope and just do a couple of the and some of these things you can follow along. So what I'm going to do now is we'll just kind of start with some image loading in an AVM tagged image. By the way, how many people here know what AVM tags are? Okay, so AVMs is a metadata standard for most image file formats like JPEG and TIFF that use some of the same parts of the file that would contain things like the date it was taken and the copyright and that sort of thing, which are already metadata within those files, and allows you to put astronomical coordinates and other astronomically relevant metadata into those files. So there are different tools to do that, and one of the great things is some observatories and data providers, when they create, and I know this is something that you can talk to Lars about that from his perspective, but it's for people who've done the work to put AVM tagging into the pipeline, especially at press release type institutions. They could create at the end of their pipeline an image, but the image would have all the necessary information, such as if I open it Worldwide Telescope, it would put it at the right place in the sky, and that's a very powerful way to. So you send an image around, an email, you find it, and that image has this extra information that shows you how to do that. So we're actually going to do that as a test, or if you want to follow along, you can kind of do it your own. So I'm going to go to the biggest kind of aggregation of these AVM tag images is a thing called AstroPix. So let me get at Caltech. So if you go to AstroPix, you can browse images. So if I take now not all these images would have, like, for instance, this image of a spectral line or these sort of things wouldn't make sense to actually put on the sky, right? Because it's not meant to be a coordinate kind of or a sky image, but many of these are. So if I look at actually let me just look at. Okay, so if I take this image of ARP22, if I want to cheat, you can just click on View in Worldwide Telescope, and that's easy. What it'll do is, right now what it's doing is it's opening Worldwide Telescope web client, and I'll get this in a second. Next thing I'll do is talk about what the difference is between the web and the desktop client. What you're seeing here is the web client, and it's taking that image and it's displaying it in the web client. So you have the access to all this kind of image contextualization and image changing the background and foreground. So this image is placed in the right place in the sky, the same kind of crossfading, but this is not crossfading between data that's in Worldwide Telescope. It's actually, this image was loaded into Worldwide Telescope via the web client, and because it has the AVM tagged images, it was able to do that connection. So I'm going to show you a different way to do that, and that is I can go over here and take the largest of the images that's available. So I think it's this one. I'll say copy link, and then if you go to worldwidetelescope.org under develop and import image, that will just take a second to load. That will give me a page where I can paste in a URL for an image. So if I paste in this URL, it's pointing to this to the JPEG file at IPAC. It's then loading the JPEG file onto a server in the cloud. It's looking for the AVM tags, which are there because that's the AstroPix database. Kind of aggregates images with the AVM tags, and then it puts that file into the right place in the sky. So this actually, although it looked very similar to clicking on the button that said View in Worldwide Telescope, this is doing a slightly different pathway where it actually, again, transfers the JPEG into the cloud. It figures out the AVM tags, and actually it tiles the image into this toast format. And then if I say, after I've done this, at the bottom, if I click on this, it actually will save it's called a WTML file. It's a collection file for that actually contains that image that I can load up or send to other people. It's just a reference to it. If you want to look at what it looks like, you can actually so I can go to downloads, I think. So I open it with Notepad. So this is what the file looks like. It pulls so all the like the name, the RA, the deck, the zoom level, data set type, all those things that are there. The credits URL, credits are ESO. It has a credit URL which points back to the press release. All of those data are created in this process, and this is the entire collection. And so if I were to send this file to you, you could click it. It would open up a Worldwide Telescope, and again would reference it, and you could also embed it for another tour or some other purpose. So it's a great way to exchange data sets once you've loaded in an image, because the data live in the cloud. And so really it's the cool thing about it is you don't have to worry about where it lives. You don't have to worry about the server to keep it up. And Worldwide Telescope team through NSF and AAS pays, and Microsoft is paying for that storage, and which kind of relieves you having to worry about that. So again, that would be another thing that people have images and I can also load in FITS files. I'll kind of skip over that because in the sake of time, but if you have FITS files, there are ways to either load it in directly into Worldwide Telescope or transfer it into an image file with color and a little more customization of kind of a data mapping, and then show that in Worldwide Telescope. So so let me go back to the PowerPoint. So just a quick note that there are two. I mentioned the desktop client is very powerful. It has very advanced rendering engine. That same rendering engine is actually available in a new web client called the WebGL client of Worldwide Telescope. It looks very similar. We're right now, the American Astronomical Society is very interested in doing this as a in the web, because although around this table I see a lot of Windows machine, in the United States, if I were at a similar workshop, I'd see only Macs or Linux machines, and so they wouldn't be able to run the Windows desktop, and so the web client is really important for that American audience. But it has a lot of the capacity. The rendering is very fast, but the data layers, the thing that actually is relevant for this workshop, is actually it hasn't been implemented yet, although that is work in progress to do it in the web client. So if you want to load in complicated data layers, the stuff that Mark is doing with IPython interfaces to the API, right now that has to be done in the desktop client, although the web client has a little bit of that, but when that gets completed, you'll be able to drive a one website can drive another website, or a notebook can talk to a website, and that will really change how people do things. So I'm going to kind of spend a little bit of time talking about the making tours. So a tour is simply capturing a view of the sky or of the solar system, and then sequencing together a bunch of these different views, and then it's like the camera will fly through that path, however I do it, and then I can save that, mail it to somebody else. I can use it to create a planetarium show. I can use it to create one of the things, if I have time, I'll show you a Worldwide Telescope video abstract. Again, it's a video abstract is a name that we're giving to. Essentially, if you took an abstract of a professional publication and you read the abstract of that paper, and then you used Worldwide Telescope to create visuals that then represented what you were reading, and then you watch the video instead of reading the abstract. That's a thing that could really help out for journal clubs, help out for presenting to the public in other ways. But that you do all that creation of storytelling in these different clients. So I'm going to actually just kind of walk through a little bit of how that works. Let's see. Oh, it's over here. Okay, so we'll just start with a simple tour. So I'm going to, I guess I can see it over here. I'm going to get things kind of set up. I'm going to do this for the sky mode, and I'm not sure what the, obviously if you're doing this real, the story is everything. So I should think about what I want to say. So right now I'm going to, I don't know, look in this part of the sky towards the galactic center. I'm going to say guided tour, create new tour. What's it called? Test. I can give a description. I can give a thumbnail of my organization or my picture. If people want to have recognizable, kind of remember the author sort of thing. People can connect with me. One of the things that the American Astronomical Society is looking at is there's a taxonomy here for classification that is actually there's a project called oh god, now I'm forgetting. No, I'm blanking. Astronomy. Oh, no, it'll come to me in a second. But basically, it's a taxonomy that is for the professional publications in astronomy, and that will. We're looking at integrating that into this. That way, there's a one-to-one mapping between the keywords and so forth in our professional publications in APJ and APJ letters and Astrophysical Journal, and what you see in Worldwide Telescope. Right now, the taxonomy was designed for Worldwide Telescope more for an outreach audience and isn't really as appropriate for a research audience. So that's I have this test thing. I'm going to start. Click on new slide. and it does a couple things. When I click on new slide, it creates a thumbnail. It may be hard to see from the back, but there's a thumbnail of that picture view, and it also sets the start camera position for that slide. The simplest way to think about Worldwide Telescope, there's a start and an end camera position for every slide, and so that created the start one. If I want to zoom in, I'll actually what I'll probably do. Let me just click on this. So I'm going to kind of say that my final part of the slide is going to be here. I'm going to right-click and say Set End Camera Position, and then I'm actually going to pull out to the full view and say Set Start Camera Position. Now, if I just push play, it's just going to create this smooth zoom in from the one camera position to the other. And then once I get there, I can say the next slide. I can click on Add New Slide, and now I can I can zoom further in. I can say Set in camera position. I can put some text. I'm going to say like pillar. I think I'll change the color. Oh, the color mapper's over here. Make it dark blue. Make it a little bigger. I can also make it add a shape. And now if I do the whole thing, it's going to zoom in, and then, and by the way, you see there's a time underneath each slide. So I'm taking 10 seconds, which is the default to zoom in, but I can change that, and I could make this thing appear at any time. I don't really have time to do that right now, but I could have these overlay elements come and go to label things, again, for the storytelling aspects. So that's how you do it in the desktop client. Then if I kind of show the same thing, what the web client can do, this is actually something it can do pretty well. So if I go to web client, so if I go to a website and say interact, there are two different web clients. One is a preview WebGL. That's the one you should probably use for. That's the one that we're actually AAS is working on right now. So I click on preview this web client. It's going to start up this the interface. Again, the graphics engine is the same, so you have the performance should be very similar, but because WebG, as you see, the kind of moving around, it seems pretty similar. So I go to similar idea. I just go to guided tours, create new tour. Actually, new tour is a fine name, so I'll stay with that. And then again, if I kind of move around. So I'll double click on this object, and then I'll say add new slide. I'm going to say set in camera position. I'm going to pull back out, and I say set start camera position. And again, just the same way I could test it before. I've made this little tour. This zooms into that. I can control constellation lines turning on and off and the overlays in the same way as I was doing for the desktop client. The cool thing about this is I can author this on an iPad or a phone in principle. And so the ability for one of the cool things is I could do this. I could take this into a school. I could have the school kids do this on almost any device that runs a web browser, and then they could take the same thing and they could save it and then take it into a planetarium dome or a big classroom or a big screen and see their final tour on the big screen in their. So actually the outreach aspects is you can have high school kids either pull in new data sets and make their own tours. So I think that the ability to do this user-generated content and then sharing via social media or bringing into a scientific context where they can have interaction with scientists and be talking about the data sets themselves is really powerful. And I've done this before at I know at Adler's done it. We did it at Northwestern. It's been done actually all over the world in this sort of having the users be a part of the production process. So the thing that, just so you know, the thing that doesn't work right now in the web client is the 3D solar system. So being able to fly into planets and the 3D cities and the terrain, that doesn't work right now. We're working on that. But hopefully, certainly by the end of the year, but hopefully sooner than that, all those will be done. And then the web client will be very much feature parity to desktop client. And then again, you can think about doing this on almost any device without having to run it on a Windows machine, which is going to be fantastic. So that's kind of a simple tour building. I'll show you one quick thing, and then I think what I'll do is I'll show you a quick tour of it was done for a video abstract for a paper. But one more thing, just to show you, just one advanced thing. If I wanted to have really fine control over objects, like let's say I want to, instead of having these labels on the entire time, I want them to fade on at a certain time. What I can do is I can right click on this and say add to timeline. Oops. Now this creates a timeline. Normally in Worldwide Telescope, there's the state of the viewport at the beginning of a slide and one at the end, and it just interpolates from one to the next. But there's another way where I can control every frame-by-frame aspect of any object, any property of any object. So in this case, if I want it to be, if I want to have fine control, I've added the arrow, which you can see here, arrow 1 to the timeline. And so if I move this, so here I have this kind of fancier slider to move things around. But if I say, I don't want arrow 1 to be visible at the beginning, so I click on this little box, it opens it up. It shows me all the properties of arrow 1. If I click on alpha, the transparency, I click on this tiny little box and make it 0. That means it's in this kind of nomenclature. 0 means it's not transparent. And then I move the time slider over, and I say at 4 seconds I want to have it start to be transparent. So I click on alpha, I add a keyframe, and then that'll make another 0. And if I move the slider over to 5 seconds, add another keyframe, and now I click on that keyframe that I've added. Again, this is for the alpha. And now instead of 0, I say 1. Now if I I'm just going to play this part of the thing. But if I push play, what's going to happen is right about now that element will fade on. So I can have frame by frame control over anything. It can be the camera, it can be elements turning on and off, it can be transparencies, it can be different characteristics of it. So at this point, I think I'm going to stop and I'm going to play one kind of cool tour that we did for a video abstract for the Planet 9 discovery. And by the way, it's asking me right here if I want to save changes because I did actually make a little tour. I'm going to say no. If I go to So this is a tour that was showing the video abstract for the paper that announced the possibility of this new Planet 9. Does this have sound? Do you know if there's a way to get audio through the system? Is audio set up? If it's not, it's not a problem. But if it is, or I guess I can just push play and see if it works. Do you know if audio? I could do that if it doesn't work. it's going, if it goes through HDMI, if not, I can just make it go through the. Is it here? Not here?
Yeah. Oh, maybe. Yeah.
Okay, let me try that. Let me try one more thing. Let me try this microphone. Okay, I'm just going to hold the microphone up to my computer. It should be good enough.
Icy debris beyond Neptune, known as the Kuiper Belt, is gradually unveiling a population of small bodies whose orbital periods span thousands to tens of thousands of years. Remarkably, this aggregate of distant objects exhibits large-scale collective structure that is strikingly puzzling within the framework of the present-day 8-planet solar system. Namely, the most distant orbits of the solar system occupy roughly the same plane and have perihelia that are approximately collinear. The clustering of the apsidal lines and of the orbital planes of the Kuiper Belt objects cannot be explained by an observational bias alone and is highly statistically significant. What sculpts the intricate arrangement of the distant Kuiper Belt? Numerical simulations reveal that an approximately 10 Earth mass planet occupying an eccentric orbit with a period of 15,000 to 20,000 years can naturally generate the observed confinement of long-period Kuiper Belt orbits. This inferred member of our solar system, Planet 9, likely resides in the same moderately inclined plane as the distant small bodies themselves. However, calculations reveal that its orbit must be anti-aligned with respect to those of the Kuiper Belt objects. Unexpectedly, gravitational torques exerted onto the Kuiper Belt by Planet 9 also generate a population of highly inclined, large semi-major axis centaurs via the Kozai-Lidov effect. Continued analyses of both distant and highly inclined outer solar system objects provide the opportunity for testing the Planet 9 hypothesis, as well as further constraining the orbital elements and mass of the distant planet.
Okay, so that was the first author of the paper, Konstantin Batygin, reading the abstract of his astrophysical journal, astronomical journal paper, and then he and I worked together to create the tour to show it. Actually the cinematography for turning on and off the different orbital lines that actually was done by Robert Hurt at IPAC, who did that, used Worldwide Telescope to create the press release for the paper. So Konstantin has used this video for his professional use. The tour is available, so if I wanted to take the tour, and you'll actually see this. I think this will be shown at the dome in the dome session this afternoon. You can see the same tour in the dome. So it has if you're a researcher, you get your data into the system for a press release. And then it got turned into a paper, a video abstract, and then it could be used in a dome. It also can be used for professional talks. So it has this kind of whole life cycle of the data set that kind of gives the work, it's a fair amount of work to get things in sometimes, but knowing you have so many ways to reuse it, it makes it very, very powerful. So I think that's really one of the great things about it. So and that's another kind of practicum thing. If anybody has, as a researcher or knows of a really, really important paper that you wanted to kind of try to create a video abstract for that with Worldwide Telescope, we can try to work on that this afternoon too. So I'm going to try to wrap up in just a minute or two. See if that we shut down. There's one last thing, and I won't go into this in too much detail, but in Worldwide Telescope, there's, if you go to the web over here, there's a thing called Communities. If you have a Windows ID, which I think with all the Windows machines around here, I assume most people do, if I click on, it actually wants me to leave this page. Yeah, I'm not sure. I think it's just slow to sign in. Okay, here it is. Yeah, somebody's slow about that. I won't spend too much time on this, but there's basically a way to create a community. Oh, there it is. Okay, so I'm signed in here. Now that I'm signed in, if I go to Communities, it's a way to see a kind of cloud storage, and I go to My Communities, and this will show all communities that a community is sort of like a web, like a YouTube channel or like a Dropbox cloud type thing. So like I made a community for Data to Dome for this workshop. So if I click on Data to Dome, then in the community, again, there's either my computer Wi-Fi is kind of slow. I'm not sure why it's taking so long, but in this Data Dome community, I put all the tours. I can put videos, images, scripts if I want to do scripts, and those can be shared with other people. So if people want to join this Data to Dome community, I can show you the practicum how to do that. You basically go to worldwidetelescope.org, click on. You have to again log in with your Windows Live ID, and then search for this community. It's most recently created community. That's probably the easiest way to find it, and then ask to join it, and then you have access to read and write from it. So if an organization wanted to have one for their organization and have different people contribute things to it, different people could add to it. So one of the things that I want to do in Fort Worth, for instance, is to create a community of for kind of rapid science. I'm calling them science shorts. Like a 1 or 2 minute, and I have another example of that at the Dome session tonight. A 1 or 2 minute type quick. You're taking a press release, instead of reading the abstract, you're reading the text of the press release with a little bit of more context, and then showing the images, zoom into it, do a crossfade or something very simple, but do it very quickly. And if that can be done, then we're able to make little kind of pre-show, kind of science shorts that go in front of our normal planetarium shows. They'll be showing recent scientific discoveries. And so if we can, if I want my museum to be kind of creating those, and we're going to put them into a community, if people want to also join that community, they can either pull it out to use them, or if they wanted to also put it in, they could contribute to it back to that community. So that's all I have for my talk. I guess I have maybe a time for a question or two, if there's anybody has any questions. Yeah. Yeah, I meant to go into that, but yeah, I'll just show you really quick how that's done. There's so under guided tours, you say render to video. Oh, actually, that's not save as. And then, again, for some reason, it's over on this screen. And here, I can say I want a dome master or a flat. What this is doing is it's going to render them as a sequence of PNG frames, and then you have to actually do the encoding outside that. But yeah, so and that's how I got I rendered out the video for the video abstract and one of the science shorts. I'll show that tonight, but that was done on my computer here. And you can actually render out up to 8K if you want to do even large images. Yeah, good question. Yeah. Yeah, it's a digital sky survey, yeah, 4-color.
Color nature rather than how the stars look. And one thing I was wondering, has anybody tried to take the star database? We have one. But to layer that over so that you have a finer control at the different scales of thank you. So you might have finer control over the different scales of how the stars look for the different zoom factors.
Yeah, right now we have our Parcos as one data set you can do as an overlay layer, and we're working on getting Gaia in. Of course, then like you say, it then gives you ability to turn knobs to render the stars differently to make it look how you want to. So I think that's something that I want to see the system do over the next year. We'll have to see whether I think Gaia data will be the right data set to kind of wait for, and when that's there, having enough stars to really make that almost replace. Some of the deep sky stuff, I think you still want the nebular emission, but that ability to turn the star rendering once you have everything stellar is something that would be great to add in.
Thank you.
I was just going to say that our first workshop after lunch will be how to make a high-resolution texture using the Gaia data. So we could put that in Worldwide Telescope by the end of the day.
Good point. Any last questions before we take a break? Okay, we have, 10 minutes? Is that all right? Yep. Okay, thanks.
Museum of Natural History in New York, and he'll be telling us about this new initiative called Open Space, which is a very exciting project and sort of a new way to visualize things in the planetarium.
Thank you, Mark. I also want to thank NAOJ. I want to thank Satomi for setting all this up. She's carried a lot of work on this. And I want to thank you all here at NAOJ. And Mark for putting this together. Can we have the lights down? I don't know how to do that. Yes, thank you. And Mark, we're trying to gain 5 minutes, so when should I go to questions? Great, thank you. And looking forward to having this workshop here and to try a particular mission from Japan, which I will talk about a little later. It is my hope that mission visualization, which is one part of open space, can be utilized, can be used here in Japan to help us build out what we're showing already with this tool. And we received, I'll talk about our NASA funding as well, so that we are primarily we've completed our first year of NASA funding. But we've also visualized the European Space Agency's Rosetta mission. And so we're really looking at this platform of open space being something that's global. So this is me. I'm Carter Emmart, and I'm the director for astrovisualization at the American Museum of Natural History in New York City. And I have two jobs in that. One is to be the director of our space shows, full dome space shows. We've only done 5 in the, 17 years of being open. I count 6 I'm looking at Ryan, because Ryan was with us for a while. We did Field Trip to the Moon, which was a children's show, but it was a smaller show. And also the collaboration that created open space with Sweden's Linköping University. Also had the great honor to direct their opening show called All We Are, which was looking at the full scale range of the universe, which is like the movie Powers of 10. So I will show examples today of mission visualizations, and that's what the workshop will be about. But I also wanted to just give you a little bit of background. Our website, we wanted .org, but that was already taken. So we are not a .com. We are not commercial. So I was opposed to this, but this is our website if you are interested. So openspaceproject.com. I will also show some URLs later, which feel free to take pictures because of elaborate designation of the URLs. Some get complicated. But open space was meant to be a sort, in a way, a follow-on. It is a continuum of the work that created the company SCIS and the software Uniview. Uniview stands for Universe Viewer, and Uniview stemmed from work at the American Museum of Natural History with Linköping University. That's the LIU that we see there in the third line. as this academic collaboration. I met Professor Anders Innerman from Linköping at SIGGRAPH in 2001, just shortly before 9/11 in New York. And out of the collaboration, we had a very good collaboration for about 5 or 6 years of students coming from Linköping and taking on goals that we wanted to visualize on the dome interactively. So we wanted an interactive tool, in addition to our space shows, which are just a linear movie. And so I started working with Anders' students, and that was this academic collaboration. The idea was that UniView would be a freely available open source project, and it became a company. And that's fine, they've done well, but we kind of wanted to Anders and I wanted to get back to this idea of being freely available for classrooms all around the world. And we've seen some great examples of Doug's presentation of Worldwide Telescope, having that as a wonderful tool. We want something that is freely available. We also wanted open space to be something that UniView was not. I don't want to be too critical, but to have it modular and scalable, so that we wanted to be able to build it in a form that was easily modular. I think I would have an argument with SCIS if I said it's not modular, but it's just that the architecture was something that we wanted to focus on and spend a while on building. And we're still building that. And we're still having issues, as Toshi pointed out earlier, Takahe-san pointed out that what we distributed for the workshop later today had some problems with the size and the zip file, and there are dependencies. What I'm saying is open space is still very developmental. We've had our first year of NASA funding, and so it's to some degree still beta, but definitely non-commercial, with an emphasis on visualizing dynamic simulations volumetrically, and also N-body, solar system, mission visualizations that we'll get to later. But this idea of visualizing dynamic simulations is the sort of cutting edge of research in data visualization. So that's what we're talking about here. Multi-scale, just as 4D2U, just as other tools, UniView, and now SkyScan's Digital Sky 2, and the Digistar line of Evans and Sutherland, also RSA Cosmos, all do this scaling ability to go from a planet all the way out to the cosmic microwave background. But we, to some degree, pioneered that at the Hayden Planetarium at the Museum of Natural History, because we wanted to be able to interact with that, not just in production, but be able to come and go across the scale range of the universe. Our Digital Universe 3D Atlas is a compilation of all these different data sets, just as 4D2U has. But that idea of looking at that is primarily a static data field. But we wanted to really have this emphasis on simulations and visualization of time. The timeline is a very important factor here. Also, scalable graphics, and what I mean here is that we inherit something called SGCT. It's simple graphics cluster toolkit. I always get that wrong. I get tripped up. That was something done at Linköping University and made open source. And we inherit that so that we can use that to run domes, power walls, and also VR stereo. So we get that for free in the open space package. and also, as I'll point out, network features so that we can do global events. Just to open up here, these are some of the students on open space that we began with, and but new students are coming in, and I have 2 new students who I met just before leaving for a month of travel that I'll be going back to on Saturday, working on Mars data. But I just wanted to emphasize that before we got NASA funding, that these students are the ones who take on doing code as their master's thesis projects at Linköping University. So the Science Mission Directorate at NASA had put out a cooperative announcement notification of funding in 2015. We applied for and got 5-year funding that, as I mentioned, we've already completed our first year. The emphasis of this is these categories here. We have solar and space physics at NASA's Goddard Space Flight Center and the Community Coordinated Modeling Center for Space Weather Monitoring. And we were working with them just prior to the NASA funding. Some of those students you saw had gone down to NASA Goddard, and we had to be quite creative in their funding. But now we're further enabled by this. But we looked at solar space physics because they have a ready set of data, volumetric simulations that we want to look at. Missions, robotic missions, but also the International Space Station. We want to see that. We want to see all these features. We want to see the planets as they really look from space and from the surface. And so we have just completed last year in our last cycle our first round of multi-scale globe browsing. And this multi-scale means the idea that we're going to go similar to what we just saw with Worldwide Telescope to come down to, well, see buildings on the ground. That would be one thing for the Earth. But my students right now who have started in New York are working on the navigation camera for the Mars rovers. They take stereo images of Mars to move the rover about. And so the idea is to go from a global data set of Mars and come right down to the rocks on the ground. And one student of mine, a few years ago, high school student, had gathered together a group of young ladies to actually calculate using a NASA photogrammetric software an entire data set of all the micro-imager stereo images so that we can look right down to 30 microns per pixel of stereo-based models that we want to see contextualized. Astrophysics, I talked about this in the terms of solar physics, but when you have this amount of data and this amount of contextualization, you really do need to network in the scientists to tell you what to look at and look for, especially in public presentation in planetarium domes. I think seeing, as Mark was showing, that all this great amount of data, we want to be able to visualize but think like scientists. We want to be able to take that thinking and turn that into the explanation and guidance of the public, so that the planetarium or the classroom can invite in the scientist from wherever they are in the world to help explain to us what we're seeing. So the NASA funding also extended our academic collaboration with New York University's School of Engineering and the University of Utah, the world's largest data visualization facility, the Scientific Computing and Imaging Institute. And I began the month of February. We had our collaborators meeting out there with Chuck Hansen, who leads this group. And so we were looking at early versions of open space in VR, similar to a few of us saw last night with 4D2U, very exciting, as well as other projects such as
reading in the latest satellite data so that we can get updates as to where all the satellites are, or space debris, things like this. Open space we have under the NASA grant. These are our 7 main partners across the United States. And of course, Adler Planetarium up there at the top, Mark. So we like this. Yeah. So anyway, yeah. To give you an idea of what I've been talking about, just to show this was some early results. But what we're looking at is the density of the of basically the solar wind coming out from the sun, the sort of rotating sprinkler hose. I'll just run that one more time. And we see a coronal mass ejection. We only see it statically in this case, but the idea is to move around it and change the transfer function on the fly, not as a pre-rendered movie, but as something that we have in our own control. For networked events, we did this. Here's Neil deGrasse Tyson. This is Fran Bagenals, one of the scientists from the New Horizons mission to Pluto. But on the bottom in this Google Hangouts, we had about a dozen sites globally to actually see what was going on when it was happening during encounter. Right here is Mike Smale from Chicago Adler. Over here is Bolzano, Italy. This is Brisbane, Australia. That is Sweden. They had some problem at that time. This is a scientist, Fran, and my student sitting next to her who did the visualization for New Horizons, Michael Marcinkowski from Poland. I'll just run that one more time. That he is over to her left, well, that's him over there, our left, her right. And this is Jeff Hainstyles, who had done the production for, he's one of the producers for Carl Sagan's Cosmos series. But we wanted to create an event while this was happening, and we wanted it to truly be global. We called it Breakfast with Pluto. But if you were in Europe, there's, right here is Hamburg, so Dr. Thomas Kraupe, and former president of the International Planetarium Society and his group there, so that we really had this range. It was lunchtime with Pluto. And if you were in Asia, Toshi Takahei-san was connected with friends, and also Singapore. Well, Brisbane was even farther east. It was nighttime or dinner time in Asia. And this is what it looked like. We didn't have the images yet. So our museum, my museum, I had to kind of fight with the museum to say, we have something to show, which is have the scientists talk about what we expect to see. But just because the pictures are not available does not mean that there's not an event to be had. Oh, and this is Ghana. We had Ghana in Africa connected with the small home-built planetarium in Accra that Jacob Ashang has put together. So let's just look at this. What we see, this is a reconstruction. That is just a section of the path. It's called the core of observations. That's the Pluto system up top. There's an instrument view looking almost 90 degrees away, but the New Horizons spacecraft, okay, we see its labels here and all that. The starry backdrop is correct. That's from the digital universe. Our Hipparcos, our filtered Hipparcos set, it's magnitudinally complete down to parent magnitude of 7.5, I believe, so it's 24,000 stars. But here we see the trajectory with time marks, the view frustrums of the cameras, the shadows in light gray, and we're seeing the systematics by rotating it in front of us so that we see the trajectory goes past the orbit of Charon for dynamical sweeping. They were worried about possible ring debris when they found the outer moons of the Hubble Space Telescope. And the mission is designed to actually go through the shadows of Pluto and Charon. And if you look close, you see that the shadow of Charon is not yet upon the path, because time, everything is in motion. This was the best map we had just up to the day of encounter, and we're looking at one of these sort of late phase of, we're coming into the encounter phase, the closest approach. We can see the heart, and then boom, we take the image. You'll also notice a little bit of uncertainty, that edge is not perfect. The spice kernels had to be predicted. They had to build the observation sequences according to their best knowledge, and there's always uncertainty. But this is after the images came back. They're not posted yet officially in the scientific archive, but thanks to Alan Stern, the principal investigator of the mission, felt that for public relations they should release the images as JPEGs, and they're not all tonally balanced. They will do that for their map making, but we can see a difference in tonality. That one's kind of dark, but what it helps us see is the mosaicing, the mosaic nature of this coverage. And as we get closer with this fixed field of view from the long-range imaging camera, the LORRI camera, we're seeing greater and greater amounts of detail. What we want to show is how we do science. That's the idea with open space. And this week, this is around 10:10 UTC. So this is morning in Europe, and we're coming in, and this is this stereo mosaic, they called it. The stereo mosaic was built on the idea that they're going to have multiple coverage as New Horizons sweeps past. So that multiple coverage will be used to generate a height map using photogrammetry. The imaging team leader is a good friend of mine. He's coming to talk in New York on the 13th, so we have, when I get home, just about a week of preparation with this, as we will present this with him, and he will guide us as to the interesting results. But this imaging sequence had to be designed years before they got to Pluto. We're seeing multiple camera views here. We can choose to turn them on or off in open space. We're only showing image results from one camera, so it makes sense, perhaps, let's just see that camera. There's also alignment issues. I'm not trying to, mask that. It's just, once again, the uncertainty. And so NASA, after flying by, they discovered they got there, I think, 90 seconds early, which is kind of funny. But even 90 seconds early, they had to refine, based on the pictures, these navigation kernels that I want to talk about, that we will hopefully use this afternoon. We wanted to take what we had done for Pluto and apply it to a very unstandard geometry. In this case, Comet 67P Churyumov-Gerasimenko for the European Space Agency's Rosetta mission. Notice how the image we retain until we snap the next picture, while the camera view is cut off, coplanar with the center of the object. We did that because, in this case, later in the mission, they're going to pull away as Churyumov-Gerasimenko is outgassing, and we wanted to be able to see that outgassing with an image frame. We can turn that image frame on or off. But in this case, we're seeing the trajectory thanks to the ephemeris, which is published in what's called spice kernels. I'll talk a little bit about that. When I first saw this, I'm sure maybe all of you said, wow, how's this thing doing triangles? but they were feeling the gravity of this very low mass, small object to get in close and finally be able to be close enough to orbit and then drop off Philae. But once again, we wanted to be able to look at this systematically to try to understand how we actually explore these worlds. So the ingredients, think of cooking, the ingredients for space mission visualization are basically three. Models, a model of the spacecraft, a model of the target. In this case, you just saw 67P Churyumov-Gerasimenko. But then the ephemeris, telling us where everything is and when it is. And so for that, the SPICE system was developed at NASA. In one of our productions, we visualized the Galileo mission to Jupiter. And there have been attempts to reconstruct, using SPICE, the orbits. But in the early 90s, they did not yet have SPICE. What is SPICE? Well, it's an ephemeris generation tool, but they can publish out the predicted positions in time, and they use a Chebyshev polynomial expression to interpolate between in time. So the ephemeris in SPICE format, SPICE stands for spacecraft, planets, instruments, cameras, and events. That's sort of what it means. So it's more than an ephemeris, because you have to know when are the pictures taken. So in the case of the New Horizons pre-visualization, think of Hayabusa 2. We're going to another asteroid, but we only know perhaps what it looks like by radar. In the US, the OSIRIS-REx mission, also going to an asteroid, that we should show the asteroid as best we know, which is really kind of a, not by adding detail, but showing how poorly we understand. That's why we're going to these places. And that the pictures will come later. So in that visualization where everybody's excited, we were at Pluto. You just saw yellow squares. At that time, those yellow squares are very exciting, because you know later that day that one image is going to be sent back. Since it was breakfast in New York for Pluto, I rented a car and drove down to the Advanced Physics Laboratory at Johns Hopkins University and saw that first image come in. And the NASA administrator was there. Former astronauts were there, and the whole mission team was there, and everybody's hugging and jumping up and down. And there were children who were 9.5 years old whose birthdays were on the day the New Horizons spacecraft was launched. So Charles Bolden, the NASA administrator, sat with the children. It was all very exciting. The third ingredient are the images. In the case of the images that have been returned, we know exactly when those pictures are taken. And if we know the ephemeris, we can then do this image projection technique. So that's what I hope that we accomplish today. The workshop focus I propose today is one that's already flown and archived. And Hayabusa 1. And I know there's been a beautiful movie made by Kosaka-san sitting right over there. But I thought today, would it be exciting? Could we do this in Japan? To actually try to reconstruct with open space a particular mission as an exercise to make you familiar with this so that we can try to make this work. I have these links, so don't worry, in the workshop we can go to these, but they're primarily, you're looking for a digital model of Hayabusa. And I know that Kosaka-san has a very beautiful model, But this is one I found for free online. So maybe we can download that and use. But then NASA's Planetary Data Service, PDS, Planetary Data Service, is the archive for this mission data. And they have Itokawa and Hayabusa. They have the spice kernels and the image data. But also JAXA has the DARTS system. And I think we should use the DARTS system today because they have the images in JPEG format, and the format that we would like to use, easy and smaller in size, would be to use some JPEG. So we can use that from the DARTS system, which was built for Hayabusa. I love this picture. It was drawn by our code developer, our master code developer, our code master, Alexander Bach. He's from Germany, but he just completed his PhD at Linköping University. And Alex is our very knowledgeable code master. And so he was guiding me through what I'm going to try to guide you through a little bit now as an introduction. And if you get lost, I get lost. I am not a technical person. I'm a director, which means I want to see this and I want to see that, and I hope the technical people can make that work. Both in our space shows, but now in this development. But this is the scene graph, and Alex is showing up at the top is a node. Maybe I can bring the cursor in. Can't do that. Anyway, up at the top is basically the sun. And then from that, we have a node that's Rosetta. We have another one that is 67P. And we also have 67P's barycenter. So this is important. You have sort of the model of the comet, but then you have to work with the idea of where the barycenter is, which is that balance point with regard to odd geometry. And then in this case, we had the Philae lander. And we had an individual model in that case. We'll just have one today. But there's the Rosetta and the Rosetta model. And there are the NavCam images, but there's also a description you need to describe. And SPICE, remember, it's spacecraft, planetary, instruments, cameras, and events. It also describes the field of view and the orientation of the camera. So it's not just, we need all this information to characterize, to portray, to depict, to visualize the camera. So this gets into a little bit of the organization, and this was me just taking a picture as Alex Bach. I don't have a picture of Alex. I should have a picture of him. My apologies. He's sort of he's reflected in the image. He's wearing a black t-shirt, of course. He has a ponytail. So we're brothers. And not really, but we're looking at the spice kernels and how we load that. This is not supposed to be informational, but this is what it looks like in his editor. I also want to call attention to something here. I do not expect you in the back to be able to read this. This will be available. And where is it available? This is a general use document. We did a hackathon. We actually called it a build-a-thon. We were working with New York Space Apps. And they've been part of NASA's annual Space Apps Challenge. And so we brought interested people, coders together, hackers, to work with OpenSpace in October. And we had two teams, and it was suggested by Mike Caprio, who's the leader of New York Space Apps, to make two teams so that they compete against one another. So we had Team Messenger and we had Team Cassini. Now Cassini has been making observations for almost a decade. Greater than a decade, 13 years, I believe. But we focused on one event, and this is important because if you want to download all the spice kernels and all the images, you can. They're on the Planetary Data Service, but then you'll have very large files. So I proposed that we do the Enceladus close encounter of, I believe, October, maybe mixing the dates with when our hackathon was, but it was 1 year before this hackathon. And it's when they brought the Cassini spacecraft right through the plumes of Enceladus. So we were looking at that, and we did Mercury Messenger. One of our curators, who you saw, he was the middle guy in the picture. You could see me and Neil deGrasse Tyson in that movie, but the guy in the middle is Denton Ebel, who is our curator for meteorites, but he's also our chair of physical sciences at the American Museum of Natural History. And so he's on the he's on the Messenger mission to Mercury, and Sean Solomon, the principal investigator, is at Columbia University, and so he's a friend to us. So we focused on these missions, and we focused on the end of the Messenger mission, where they were actually venting helium from the tanks to keep the spacecraft up. The spacecraft was wearing its orbit down, was going to collide with Mercury, but they were able to, they had run through fuel, so they were venting their helium to actually keep it up and get very high resolution pictures of the surface. So in a one-day hackathon, we had partial success. I hope we get greater success this afternoon with going through this for Hayabusa 1. And we also added another element to Mercury and Saturn. Was we had the team at NASA Goddard do a volumetric model of the magnetosphere of Saturn and of Mercury. Saturn has an enormous magnetosphere, being a gas giant. Mercury has a very interesting magnetosphere. It has a very large iron core, so the magnetosphere comes in quite close. And we could see, by visualizing the orbits from the spice of Messenger, how Messenger goes in and out of the magnetosphere on every orbit. So where is this located? Another photo op if you want to get this. I meant for this to be stuck on your flash drives, but it was in this MD format, which just came up like a bad text file. So anyway, if you do read this in, sorry for the long URL, but it pops up in a Dropbox, readable. So if I go back to is anybody still taking a picture of it? I'll leave it up there for a minute. I'm sorry it's so long. But because of the hackathon, the build-a-thon, it created a challenge for Alex as our codemaster to write a document describing the general use of open space, in particular for the use of open space for mission visualization, which I wanted us to work on today. In that, if I go back now to this document, I'll just show the highlights perhaps. There's configuration, and it refers to the simple graphics cluster toolkit I referred to in the beginning. A way to configure your view plane, your field of view, and your single viewport of a single computer screen or multiple for the dome. It describes the scene files and the mod files in the various scenes. And just, I know you can't really read this, but it goes through at least it talks about, again, written by the developer in terse language, hopefully simple and direct language, what is necessary, especially if someone understands the technical jargon. Image projection. We talked about that, how we have the images and do all that, but it is described here. And it is described how it's done. By the way, there's something up here, I'm seeing it because I'm close, I don't expect you to, but it describes something called NAIF. SPICE is part of NAIF. This is NASA. This is Navigation and Ancillary Information Format. So for those that don't speak that language, I just want to spell it out to you. For those that do understand NAIF and SPICE, perhaps, then he's referring to NAIF here as it is a greater envelope for SPICE. So, what I'd like to do now is show you what you have on your stick. What I'm going to do, I'm going to scale this so that we make everything bigger for you to see. Can you see that okay? Some in the back, can you see? Good, thank you. I will get rid of get that out of the way. So what we have that we're sharing with you today is on your flash drive, you'll have Open Space New Horizons. And I also have the Rosetta, but Rosetta was a larger directory. We may want to refer to Rosetta. Why? Because Itokawa is an asteroid and an irregular shape like 67P Churyumov-Gerasimenko. So the basic structure, once you open up Open Space, is that to run the executable, by the way, I'm running this on the Mac. It does run on Macs, but we do not have an installation package yet. And we pulled a near all-nighter with one of the developers in Utah because I wanted to be able to show you on the Mac right now what that is, bring it up and show you. But I have a boot camp Windows partition on this machine as well. I'm not going to go through that. I just want to briefly show you this modular organization. And if one opens up the bin directory, one finds the Open Space executable. It's here. Going back, there is a data directory. There are lots of directories. My apologies, this is a tedious exercise, but it will get us a visualization hopefully this afternoon. In the data directory, importantly, we have scene and SPICE right there. If we go to SPICE, open that up, I'm going to find the kernels. What are the kernels? SPICE publishes the various forms of whether it's about the spacecraft or whether it's about the planetary bodies, the barycenters, whatever it's going to track by an ephemeris. It has different categories there, and they call them kernels. There is there's an SP kernel, which is a spacecraft kernel. There's a C kernel, which is for camera. So the camera is going to ride along with the spacecraft. The camera will look around to different locations as it goes. So you have to track both the spacecraft and the orientation of where the camera's looking. So there are these different kernels. So if I open up New Horizons, by the way, we had there's New Horizons and NH. And I think that there were two different sets. I think that's why that's there. Apologies. So in this case, we have a BC, which is, so there's a C kernel, but B is binary. So, and then we have the SP, the position of the spacecraft, and we have other kernels in here. They are described in a configuration file, how they are loaded. So let's go look at that. I back up, I go into the scene file. And so in the scenes, even though this is really just loaded with the New Horizons scene, that's what's loaded on the distribution today, is that we also have these other categories in here. So, for example, I'm not going to show it to you, but LOD globes, that's from the new globe browsing, levels of detail global models. Things like that. We have, you may notice, someone may see there's a Juno scene. So we did Juno at Jupiter just as a quick one-off because, we have Jupiter and a texture map for Jupiter, and we have the moons of Jupiter, but we just took simply the spice kernels. This is what I'm hoping to do today with Hayabusa 1, is to just load those kernels for that mission, just like we did with Juno. So we could see, we had the Juno model, we could put the Juno model properly oriented because of the spice kernel to, so its solar panels are facing the sun, and then we see the Juno spacecraft going around Jupiter because the positions are described in the SP spacecraft ephemeris kernel in the SPICE system. So if I come down here, there's a New Horizons scene. I'm going to have to open that with a text editor. My text editor, and let's enlarge this. In this case, this instructs which kernels to load and in what, or actually which scene components to load, and set the term renderable. These are things that will end up being rendered, whether false or true, and various components. I do not want to go specifically detail by detail. But the idea for the workshop this afternoon would be to take the spice kernels and apply them here for Hayabusa. And I'll show you a little bit more with that. So these are the modules that are loaded at the very bottom of this scene file. Load the sun, Mercury, the other planets, okay, fine. And also the Milky Way. We have a European Southern Observatory Milky Way image. That one's commented out, I think. Sorry, Lars. I think we're using something else. But in any event, we're seeing the various components. Once again, New Horizons. Okay. Where is my Mercury? Okay. I want to speak just briefly as well about getting the spice kernels. So I showed this earlier. This was the document with the URL that you can download. But if we want to go, in the case of getting the kernel data, we can go and get the kernel data from the small bodies node of the Planetary Data Service. And we come down here, and there we have 25143 Itokawa. And we open that up, and we see, wow, these are these different things we can find. This is where we find Gaskell's Itokawa shape model. Gaskell works at the Planetary Science Institute, and created the shape model, apparently. And then we have the Hayabusa Amica, and we have the LiDAR. We have all these different categories, and we have the spice kernels. And if we go to the spice kernels, okay, ooh, this is a little difficult. Because I resized my screen. But if we look down here, we have different ways to look at these spice kernels. Remember I said if you have a mission like Cassini, you don't want to download all of them. You want to download just a part. So if we look here, Messenger, where is Hayabusa? There we are. And there's a README. Hold on, I'll slide this back. And it will describe, there's a lot of documentation here, and it walks you through a kind of table of contents. And it will describe the different kernels. Let's go back. And Hayabusa link. If I go to the link, that'll give us basically the directory structure access to everything. So if I come in here to data, oh, here are the kernels. The camera kernel, the event kernel, the frames kernel, which is or the camera frame, views, the instrument kernels, other instruments. And so these are the different kernels. If you go into one of these, let's just open one of these up. We see that there is the kernel and there's a label file telling us what they are with dates. And you say, oh, this is very complicated. Well, there's another way to look at this that they offer you. So let's slide this back over. And that's a subset. It gives you the range of the mission that they have data for. But they also give you a subsetting tool. And I've enlarged this so we can read it. But you can say, wait a minute, I don't want the entire mission. I just want a day or two. And that's what I would propose we do. And so what you do is you put in a start and an end. On the center screen, I'm seeing that. This is cut off. But, and when you do this, there are examples of what format. These are the different formats of the date formatting. So I can say what part of the mission I want to see. And that's where looking at the JAXA page, I found it much more informative. So let's go to that. Here's the DARTS page. This is the JAXA page for data. And in this case, it allows me to see I've chosen an observation date, and there's an operational phase. This is a little bit more speaking to someone like me, non-technical, what phase this is. So if I look at this, I chose home position phase. Home position over Itakawa. And so for that phase of the mission, I then have an observation date range, and I chose here. And when I look at the results, I get some nice images that we could imagine being projected onto the model. So we would see in that case something like what we did with Rosetta. So I would suggest then here we can actually, you can download the FITS images, which are, the FITS images 32-bit or 24-bit. Looking in the back row, I'm not sure because I know for I'm putting you guys on the spot, but from JAXA, but FITS image they are a higher bit range than 8-bit. I'm never sure either, so it's sorry to put you on the spot, but nevertheless. That we can also download here, a full frame image. Let's do that. That one's nice. Ooh, okay. So we end up with this image, and that's a 512 image. But I think I downloaded another one. And that one, it's kind of hard to see, but that's that's the background of dark gray, and this is the actual black of sky. And this is a 1024 image. The resolution of the image will be independent when we put it into open space. The mission is economizing on how much data they have to send back. So, maybe we take a 512 high bit range image or a 1024 image. These will be scaled to the view of the camera and properly positioned with respect to the model, which I hope that we can get to this afternoon. So, just to go back to this subsetting, once you have this date range, once you select a part of the mission we want to see, we can go back and we can submit, and it will return a wget statement, for which we will then download that to the particular machine, I believe Windows machine that we may be working with. And Takahashi-san may have, I'm not sure, we may be working on one or several machines, but hopefully that's the case. I want to see if I'm leaving anything out. I'm just looking at about 2 minutes left here. I haven't taken you on a tremendous tour of this. The demo, that would be fine for New Horizons. I think, I showed the movie, and so the movie I find is just a quick way if I'm talking and showing at the same time. But thank you, Mark. What's great is that it's working, so that hopefully we can apply that. I think in practicality for the workshop, we will download a section of the observation phase of Hayabusa 1 to Itakawa, and then we will build around that, and we will do that together. We will look at the structure of where the kernels have to be loaded in a particular order. I was looking for the New Horizons mod file. I'm looking at the time. We will do that together. Are there any questions? In general. Thank you for your attention. I hope I am understandable with my English. I hope I've spoken slowly enough. It's a lot to cover, but it's a great honor to be here, especially that I don't speak Japanese. So thank you very much.
Thank you, Kata-san. Okay, we will get a lunch break from now. Please, we may hurry up to arrive at restaurant. Maybe, okay, someone. The restaurant is over the ground. It's easy to get.
It's loading a bunch of 16K textures, which if you don't have like a killer graphics card like I do, crap.
You may remain your laptop,
Yeah, so they're like,
but not the purse, money. Equipment okay to remain on your table.
Downsize the textures, just to prove the concept.
now we'd like to start the afternoon session, but we have a couple of announcements before the start. Agata-san, talk about the CAPS information. Agata-san, please.
Good afternoon, everyone. My name is Hidehiko Hideagata. I'm one member of this Data to Dome workshop. How about this Data to Dome workshop? Enjoyed or hard or well? Thank you so much. Not me, so especially for Mark-san. This workshop is IPS and NAOJ hosted and this program mainly Mark-san and IPS person. And Ito-san and us only logistics. So, I hope to, before the Kato-san's important workshop, I hope to introduce, I hope to say welcome again next year to you. Okay, please see the provided this small seat. This my announcement about the CAP 2080 in Fukuoka, Japan. This is an official IAU meeting, IAU Commission 2 meeting, about 2 years interval. This is a 7th conference. So this conference is very interesting, very inspired and important to make the relation to share the cutting edge this information and others. So of course this includes visualization, dome session, and creating and planetarium activities also. So open this pamphlet, this paper. So Fukuoka City is the biggest city, Kyushu Island, from this place, south little west, west little south, so Kyushu Island, very nice place, and just the cherry blossom full. We hope so. Cherry blossom.
And many good paths.
March 24th to 26th next year, like this photo, a lot of cherry blossoms and enjoy star watching and enjoy Japanese classical opera, no playing and drinking a lot. Very nice. So enjoy Ohanami. So this Fukuoka City this year, August 1st, new museum, new science museum. This is Fukuoka City's sponsored city museum. So big planetary dome. So Konica Minolta 4K planetarium system and good exhibition and others. So please make good, please create good content this workshop and so show your all contents. This so CAP conference includes your presentation, your appealing time. So please come again. Okay. Okay, understand? Okay, so promise us. Okay, 日本の皆さんもぜひ全員参加していただけますよう期待してます。よろしくお願いします。ありがとうございました。
Thank you, Agata-san. And one more announcement is we'd like to distribute a piece of paper. In afternoon session, we have to divide 4 groups. So, which is your favorite group? Please check the paper, first choice and second choice, and then return to registration place. Thank you. Okay, we start the afternoon session, and in afternoon session, Carter Emmett-san take chair, and as you know, Mr. Carter Emmett is Director of Scientific Visualization at the American Museum of Natural History. And so, Kata-san, please start the afternoon session.
Thank you, Ito-san. I am looking forward to our next presentation by Kato-san. And very interested, I would like to join your workshop, but I have my workshop to work on. But it's a great honor. And last night, I'll just mention those of us who arrived yesterday saw Mitaka in VR system. Very impressive. So thank you.
And today I would like to talk about Mitaka and the 42 project, and then we will talk about the workshop and the practical. The 42 project is a project running the NAOJ to visualize astronomical data, and that is observation data, theoretical data, simulation. And there are two main contexts in the project. One, Mitaka software, and the other is movies that is based on numerical simulations. And there are many movies, and two speakers will talk about these movies tomorrow. And these contents have been used in the 42 Dome Theater, and also distributed on the web. And tomorrow you see the 42 Dome Theater. And about Mitaka software, it had been developed in the 42 project since 2003. And it seamlessly navigates through space from the Earth to the edges of the known universe. It uses various observational data and theoretical models. And of course, the name Mitaka is named after the Mitaka city here. And Mitaka is free and open software. License is MIT license. Mitaka uses a variety of up-to-date observational data. For example, distribution of stars, which are obtained from the observation by Hipparcos satellite. And this is distribution of distant galaxies obtained from SDSS project. And this is surface texture map of Pluto obtained by New Horizons spacecraft. And Mitaka also uses some theoretical models. For example, this is a theoretical model of Milky Way galaxy. And it is rendered with
real-time ray tracing volume rendering method. And this is rendering of gravitational lensing. And you can see this Einstein ring if you are in right position. And this is a model of globular cluster. And Mitaka also support dome master rendering for fisheye projection. And this is dome master. And this is a scene Mitaka in the dome master mode is projected on 5-meter air dome. And Mitaka also supports multi-language. Currently, it supports these 8 languages. And these languages will be supported. And users can add their own languages by creating and editing text files that define strings. And these multi-language strings are defined in a simple text file. And this is an example of Thai language. And the left-hand side are keys for the strings, and the right-hand side are actual strings. In this case, word in Thai language. And these files are in Unicode format, and you can write any letters in Unicode format. And these file strings definition files are stored in the locale subfolder in the Mitaka's folder. And you can edit these strings. And Mitaka is used some stereoscopic domes for scientific live shows. There are 2 stereoscopic domes in which Mitaka is used. And one is our 42 dome theater. And we will go to there tomorrow. And the other is Kurobe Yoshida Science Museum in Kurobe City, Toyama Prefecture. And in these domes, one can see Mitaka and simulation movies in stereoscopic mode. And Mitaka is free and open source software, and anyone can download it for personal use or educational use. And for users in planetariums or museums, please contact the for this project. And recently, Mitaka supports virtual reality VR head-mount display, Oculus Rift and HTC Vive. And Oculus Rift is like this. And this is a scene demonstration of VR version of Mitaka with Oculus Rift. And this is a poster for Mitaka VR version. He is Kokubo-san, Professor Kokubo. He is the project leader of the Hodiji project. So one can experience Mitaka in VR space wearing such VR head-mounted display. And Mitaka also supports another head-mounted display, 8TC Vive. And with this head-mounted display, one can walk around up to 3 meter by 4 meter area around this region. It's called room scale. And one can operate Mitaka with VR controllers. These are VR controllers. And for example, to zoom in one pinch out the VR controllers three-dimensionally. And zooming out is opposite action. Then there is a time for experience of this VR version of Mitaka today in practicum time this evening. And please operate Mitaka VR version with VR controllers by yourself. And summary of Mitaka. Mitaka is software for visualizing the known universe from the Earth to the edges of the universe with observational data and theoretical models. And Mitaka is free and open source software. So I will show you a short demonstration here. And now we are on ground of the Earth, and you see the night sky today, 8 p.m. And we are leaving the Earth for outer space. This is the Earth, and Mitaka, of course, can operate with mouse, keyboard, and controllers. And then go outer space. And this is orbit of the moon. you can see the solar system. And also the trans-Neptunian object around the solar system. And this is this distribution of stars. These data are obtained from Hipparcos satellite. And we see distribution of stars within about 100 within 100 light years. And this is theoretical model. Theoretical model of our galaxy. And these are distribution of galaxies. This is distribution of galaxy, distant galaxy obtained from SDSS project. And you see the large-scale structure of the universe. And finally, you can see the cosmic microwave background obtained by Planck satellite. And recently, Mitaka support some preset mode. And for example, you can see the approach of the new horizons to the Pluto. And also approach of Juno probe to the Jupiter. And you can also go to the supermassive black hole at the center of the galaxy. And this is gravitational lens effect. And at the VR demonstration, you can see this effect in VR space. Okay, that's all. So next, I will explain my workshop or practical. And here, instead of a workshop that specializes in Mitaka software, I will carry out a more general one. So what to do in my workshop today is to make a Milky Way texture map from the Gaia Day1 data release, first data release data with Python. The generated Milky Way map in the workshop can be used in any space engines and also for various purposes, because Milky Way texture map is just a JPEG image file. Of course, it can be used in Mitaka software. Gaia satellite is a space observatory of ESA for astrometry, and it will observe over 1 billion stars for 5 years, and determine their three-dimensional positions. And it's the successor of the Hipparcos satellite. And as you know, Gaia's first data release, DR1, was released on September last year. And in Gaia DR1 data, about 1 billion of stars were observed, and among them, parallaxes were obtained for 2 million of stars. And two-dimensional positions on celestial sphere and magnitude of stars were obtained all of the 1 billion stars. And those are sufficient for our purpose to make a Milky Way map. So we use this data. However, there are some restrictions in Gaia DR1 data. First is there are no color information in data. And the second is there are some areas where number of observations are still not sufficient. And in particular, around the galactic center, they look like dark streaks. And because of the first point, we will make a monochrome Milky Way map. These points will be resolved in the data release 2, which is scheduled at the end of this year. So what to do? Since Milky Way is just an appearance of an aggregation of stars in the galaxy, so in principle, a Milky Way map can be generated by summing up the intensities of light from individual stars one by one. So here, we simply do this with Gaia's DR1 data by generating an all-sky mean intensity map. But you may think the following question. There are 200 billion stars in the Milky Way galaxy. So 1 billion stars are enough to make Milky Way map. This is result, not a photograph. This is generated by Gaia DR1 data. So 1 billion stars are enough to reproduce such a beautiful Milky Way map. And this is close up of the galactic center region. You can see details of galactic center region are reproduced but as already mentioned, there are some dark streaks. Then let me show you outline of the workshop and practical. It is divided into 6 sections like that. First section is an introduction to Python and Jupyter notebook. And then we download Gaia DR1 data using Python from the internet. And then we extract minimum necessary data from the original Gaia data. And then this is the main part of the practicum. We generate mean intensity maps from extracted data, and then converting the intensity maps to a cube map, and finally convert it to a sphere map. Cube map and sphere map are a format for texture map. And section 1 will be finished in this workshop time. And the remainder will be done in the practicum time. So the first section is introduction to Python and Jupyter notebook. And this is Jupyter notebook. And to proceed in the notebook, enter the Python code in code cells and run them step by step. This is the Jupyter notebook for introduction section. And this is texture cell. And this is code cell. And one can enter in code cell. And run it. So as a practicum, it is recommended to type the code in the code cell. But because of restricted time, copy and paste is okay. In the second section, we are download the Gaia DR1 data from Gaia's site. Data is available at this URL. And there are 3 types of data format. Here we use zipped CSV format. And for this format, there are a total of about 5,000 of files. And unfortunately, FTP site will not be available currently. And so you cannot use, for example, mget command to download all of the files at once. But fortunately, we can download them automatically using Python instead of clicking all the links to the data files on this site one by hand. Then extracting necessary data. Each data file contains data about 220,000 of stars, and for each star, there are 57 types of data. For example, light ascension, declination, parallax, and so on. For our purpose to make a Milky Way map, only 3 data are necessary. 3 data are the galactic longitude L, and galactic latitude P, and magnitude of star. Therefore, we extract these minimum necessary data from the original data and save them into other files in the section 3. And section 4, generating intensity maps. As already mentioned, to make Milky Way map is to make the mean intensity map of star light in any direction. And here we make the intensity map in the cube map configuration, like that. And in this configuration, stars are observed at observing point O at the center of the cube. And through one of the 6 planes of the cube. And this is one of the planes. And on each plane, intensity of light from stars are summed up on cell. And finally, mean intensity map is obtained on each plane of the cube. Then obtained mean intensity map are converted to cube map image like that with gamma correction. Gamma correction is needed because display devices for the display devices, input signal and output level are generally not related with linear relation. So such a correction is needed to display on some device. Then finally, cube map is converted to a sphere map. And in this form, Mitaka can use this map. So, because of the restricted time, we cannot make the entire Milky Way map within the practical time. And so, we can make it within this region in this time. However, one can make the entire map using the same code at a later date. So let's start workshop. First, open the Jupyter notebook file named introduction.ipynb. This file is in the USB memory stick. You will get it at the registration disk. So can you open this Jupyter notebook? And you cannot open this file in Jupyter notebook home. Try the following things. First, open command prompt, and then move to your folder using cd command, and then type Jupyter notebook there. Then Jupyter notebook will be launched, and you can open the file. And this is the Jupyter notebook again. And first, please read this section. This explains the cells in Jupyter notebook. And this region, this is text cell, and it explains some topics or contents. And there are another type of cell, code cell. This is a code cell. And you can enter Python code in the code cell. And after entering some code, you can run it by clicking this play button or pressing Shift plus Enter key. And then please read this section. This explains print function. It is useful to display the status of running code. And it can be used like that. It also display values of variables like that. And then it's practical. Please enter this code in the cell below. And as already mentioned, you can copy and paste here. And to run this code, please press Shift and Enter key as already mentioned. this is the output of the code. In Python, you can write a comment with this sharp symbol. And this is a comment. And comment doesn't affect on running the code. So if you enter this code and run it, result the same result. Then for loop. A for loop for index I, which runs from I equal 0 to I equal 9, returns false. And this defines the for loop. And note that in Python, the indentation is in code is very important. It plays a very important role because the indentation defines the code block for which the for loop is applied. Then try the example of for loop to enter this code in the code cell and run it. And this is result. Then if statement. It is written like this. And like for loop, code within an indented blocks run when the condition for the if statement condition is here is true, and an if else statement is like that. This line runs if the condition is true, and this line runs if the condition is false. And then present this code in the cell and run it. This is output. And because we set A equal to 1, this condition is true, and this line is run. Then function. In Python, users can define their own functions. And generally, functions are defined as a block of code. And it can take argument as an input, and it also can return values as an output. And it can be called repeatedly any number of times if necessary. In Python, a function is defined with def keyword as follows. And the content of the function is defined in indented block. And then enter this code in the cell and run it. This code first defines the function here, and then uses the function, and output the result. This is output. And modules. In Python, a lot of functions are defined in modules. For example, mathematical functions are defined in the math module. To use functions in a module, import the module with the import keyword. And like that. And enter the following code in the code cell below and run it. This is output. This code first import math module, and then uses functions and constants defined in the math module, and print the result. And modules used in the following workshop practicum are these modules. These are very primitive modules. And all modules are available by default in Anaconda environment. So let's use the one module to download a file from the internet. Module to be used is URL lib module. You can download the file located in the internet by using Python. For this, the function URL retrieve function in the URL lib module can be used. And please enter the following code in the cell below and run it. So this is result, and this code first import the modules, and then define the URL where the file to be downloaded file is located, and then file name for output, and finally call the function, and this download the file. So please see your local folder, and if the download is succeeded, there is a file named text file .text. And then actually files used in Mitaka workshop practicum is located at the internet. And please download these files by using Python function. And the location is here. And similar to the previous example, define this URL and output file name. Please enter the code in the code cell and run it. And this code download the zip file for workshop. And it contains 5 GB notebooks. That's all for the introduction. And after downloading the zip file, make a folder for Mitaka workshop, and then unzip the download file into it. And then you can ready for the workshop and practicum. And this is outline of the practicum. I have already explained, and there are 6 sections. And for each section, there are 1 GB notebook. And please proceed each notebook step by step. Then let's move on to section 2, open the notebook for this notebook. That's all. That's all, thank you.
Questions?
Did you mention that Mitaka was open source or it's just free? Is Mitaka open source?
Open source, yes.
Where is the source?
You can download from Mitaka's website. There are page for download.
Okay. Afterwards, maybe you can show me. I've been looking. Maybe I'm missing it.
I have a question about scientific integrity. So, scientific correctness. So you use all the correct data. Some of us have discussed whether you can expand on those data using synthetic stars, for instance, or I'm looking at Makemake's surface and it's blank in Mitaka. There's nothing on it because we don't have a lot of information. So that's one approach, but what do you think about expanding it to make it more realistic in a simulated way? It's difficult to explain simpler, but your software is very correct. Could you imagine making it look better by synthesizing data, by making stars that you don't know about in an algorithmic way based on physics?
if possible, I will.
Because right now, when you move out of the local neighborhood with stars, you have this sphere, this ball of stars around the sun because of observational bias. But that's obviously not how the universe looks, right? It's the same for the galaxies, right? That you have these strips where the surveys have been, and we love that as astronomers. I'm less sure that the lay people enjoy seeing these because they don't understand why are there strips in the universe. So I think it's an interesting discussion. I can't explain it better.
I'd like to speak. Please, first.
At present, our policy, we use basically observational data. But exception is our galaxy. For our galaxy uses theoretical models have not been observed entire the galaxy.
When we started to do this digital galaxy project, which turned into Digital Universe, we had Ron Drimmel, the astronomer, who's in Turin, work very hard on a accurate statistical model of stars, and it blended pretty well with Hipparcos. But what's the use of it? I ask that question because when you fly out and you look back, that observational bias is our knowledge. And if you fill in, you don't know what's real and what's not. So there, it's nice to have both because you can sort of turn it on and off. But you did say the Mitaka galaxy is an astrophysical simulation based.
M30. M30 also theoretical model.
It's a model.
Yes.
I think you just have to be very careful and say that's a model. And it's also presenting the digital universe with, similar to Mitaka. Yeah, you see the region that's been covered and the region that's not. And in our production of Dark Universe, we chose to show what's seen and what's not. We explain that these are areas we've yet to map. And for young people, I think that's actually a great thing. You say this is your job in the future.
Well, I'm just going to say the same thing he was already saying, but I think one of the most powerful things we can visualize is how our knowledge has grown over time. But if we fake it, we lose that ability. So the idea of, we're making great progress, we're figuring out more and more, it's a really powerful thing. It's something that, at least for where I work and sort of our brand, I think that's what makes a difference between what we do and what Hollywood does.
Margaret Geller's catalog, 1983 or 4? Yeah, 3,000 to 6,000 galaxies. Brent Tully, 1998, 3,500 galaxies. He had more fleshed out spherically, not just survey that Margaret had done. Hers was low number. But then by 2000, Tully had 30,000 galaxies in his catalog, and then Sloan came out 2-degree field. So I think, trying to present it that way there's been a tremendous amount of knowledge gained. But I think you run a risk of, if you fly to Hamamea or whatever and you show craters on the surface, why not just show it blank? Say that's why we have to go there.
The most important thing is to be honest.
Yeah.
Right?
with people of your background and stature, I would hardly dare to argue against. So I'm just sitting here very timid. But I can see your points. But I also have a little bit the other view, and it is true that we do artist impressions in this business, and we kind of allow ourselves that freedom. I don't know if we're misguided when we say we lead ourselves by the physics and by the science and we present something which is believable, or if we should indeed be more blank with the surfaces of these new exoplanets that are found. I mean, maybe we have strayed over into the science fiction side, and I think it's a discussion that's very important and something we should continue to discuss because it's important we get it right. And there are discussions at the moment about exoplanets and about habitable zones and possibilities of life, and maybe we are pushing our luck a little bit, but that's a bigger discussion. Anyway, I think it's an important and interesting question, and I think also you have a point when you present something and you say this is a map of the universe. Obviously, you don't want to fill in the blanks. That's clear. You want to have that storyline. This is what we know. There is more out there. That's why we need to get money for building the European Extremely Large Telescope and other telescopes. LSST. But there are also other storylines where maybe with kids, younger ages, where you don't necessarily have the galaxy catalogs, but more synthetic distributions, and you explain the universe more as it is. I don't know. Different stories.
I was at a bookstore. They don't even have bookstores anymore, anyway, in New York. But I think it was Stan Peele's book. I'm not sure. It's looking at exoplanets, and it had a picture of what the resolution of the Earth through the terrestrial planet finder of something that's within maybe 20 light years if we found another Earth. And it was very depressing because you spend all that money and you get like 100 pixels across. We live in extraordinary times where we've flown across the solar system down to incredible detail, rovers on Mars, but where do you stop is the question, because then if you fill in the stars, you say, well, we'll fill in some planets. Fill in some planets, we'll put some civilizations there and call it the Delta Quadrant. So it rapidly becomes science fiction. That's where I felt, in our case in New York, that it was like this statistical model was problematic in showing it. Yes, you want to turn it on and turn it off, but yeah. I want the data. And Gaia was disappointing because it was just, you have your ball of Hipparcos, then you just have a denser ball. It's not like it's like reaching way out across the galaxy. I mean, it is a little bit, but maybe we're out of time. So anyway, should move on. Yeah. It's good discussion. Leading right into. So let's see, we're supposed to start now with Lars. Yeah. We'd like to, oh great, okay, excellent. Yes, please, whoever has the questionnaire, sign up. We would like to collect it in the back, please. And so we know who is signing up for which workshop. So I guess we have a few moments. Yeah, great. Thank you, Ito-san. Yes. Yeah. Leading up to Lars. Great. So I think we've talked through the break, but I guess we have a moment to get some coffee. But then we'll have Lars Christensen from the European Southern Observatory up next. the European Southern Observatory. And are you still working for the European side of the Hubble?
Also, yeah.
Yes.
So we have that, we're doing that for the European Space Agency, so
Yes.
we do more than half of the Hubble images. Not necessarily the prettiest, but more than half, so.
And then also an exciting new facility that you're overseeing.
Yep, we have a planetarium under construction also, so that's
Great.
also fascinating.
Well, let's all join in welcoming Lars. Thank you.
Thank you. So I promise there will be no coding in this presentation at all. As Mark said in his introduction, it's about making things simpler and getting the data out to the lay people on a much quicker time scale, and that's the point of my talk. So I'm going to talk about Data to Dome, which is the name of a project, not necessarily the name of the concept that Mark for the IPS, but it's a small standard, it's a much simpler thing, allowing the content to the dome directly from the data providers. And I speak on behalf of a larger group of people, some of which are here in this room, notably Mark and Ben. Also Robert Hurt, whose name has been mentioned several times, has been very instrumental for the work here. And of course the IPS Science and Visualization, Data Visualization Task Force. I have about a handful of slides just giving you the background, setting the scenes. As we all agree, astronomy is a fascinating topic, otherwise we wouldn't be here, but it's really, really interesting. I mean, there has been no time in history where we're seeing this kind of a rapid pace of discovery. Things are popping up on a daily basis. Ben and I just counted the numbers of press releases, and there's been about 3 per day, if you count every single day, including vacations and weekends, over the past 10 years. Of course, not all of them are equally interesting as, seeing the first Pluto images or any of the other major discoveries like gravitational waves, but nonetheless, there's a lot going on. And the planetariums are often seen as kind of knowledge centers, astronomy competence centers, at least by us. But it is actually not true if you look at what we do. Of course, we do a lot of science outreach and communication, but often, more than not, we actually don't get the science out there on a daily basis, on an hourly basis, what's going on and taking place. Now this project, Data to Dome, it streamlines the flow of content from research institutes. It could also stretch wider to the planetariums. And as Mark also mentioned, we start small. We start with things like images and videos and press releases and blogs, and then we can build on that to the bigger point clouds and galaxy surveys at a later time. Why is it not really happening yet, or hasn't happened yet? And that is that it's really a lot of work. It's a manual thing to overcome, copying content, slicing and distributing to the render nodes and writing scripts to get things in, working in Python and whatnot. But there must be easier ways. And often the content is not standardized. The pipelines and procedures are not very easy to work with. They are different from vendor to vendor, and things are scattered all over the internet. They are not necessarily simplified or curated or easily found. So Data to Dome relies on a standardization of the formats and the processes and a consolidation of the data and metadata, and some staff curation, some ranking, and some distribution via the internet, bringing all this together. Every morning, the presenter can go to his console, her console, and actually act as this astronomical weatherman, which is kind of the mental image that we have. Not necessarily as entertaining, but at least someone who has the information at hand, who knows when things are going on and what's going on. Also, if some little 12-year-old girl pokes up the hand and says, what about this thing that happened I just saw on TV last night, then you have to be there on the ball, and you have to actually be able to, within a few clicks of a mouse, to pull it up on the dome, and if nothing else, then pretty much read off the main information which has been put out with that particular news story on the screen. The data, so we start small. There is the metadata part, and then there are images and videos, full dome videos, audio, 3D objects, maybe some show sequences also. The show sequences we haven't come to yet, but maybe that could be one of the next things. This is kind of a diagram, a quick and dirty view of the different components that we have. It starts with the content that's here. And let's say we have an observatory like Subaru. It's a good example, a Japanese example. We have a database of something, in which case it could be images, maybe you have videos also, but you do need a database. So that's the thing where it starts. You have to describe that data with metadata and be able to deliver this to the planetarium vendor through a JSON feed. So that's the magic word, the JSON feed. The vendor can then take this information, make it searchable. The vendor needs to archive it somewhere, rank it, the thing that makes Google famous. Not easy to do, but nonetheless has to be done. And then allow for some sort of quick drag and drop presentation on the dome. Then we have this data to dome concept, which is nothing but metadata standards, data standards, some coordination, some communication. Like me being here today, telling you about it, that's part of what we do. And then getting these data and metadata into the planetariums, who can then deliver great live science with one click. And that's pretty much what's described here in this lengthy slide. So let's leave that for the PDF you can read at home. Now, what are the use cases? Well, I already mentioned the press release. You have a new exoplanet system discovered, and you want to actually talk about this pretty much at the time of the release, when things become public, because people will want to know, and they will be informed from their radio station and the TV, so why not also the planetarium? And that's the point. The news has to appear on a screen with the presenter, who can then decide to pick it or not for the Sky at Night module or whatever kind of programming that fits, and present it on the dome. It could also be a lunar eclipse, something that comes up and is on a sort of event base, a timed event, which you then pick and decide to present on your dome. That could be full dome videos presented as well, showing that particular eclipse. It could be combined with the standard planetarium functions, also something we haven't come to yet, but that's an obvious thing to do, since you have much more in a planetarium system than just presenting images and videos and full dome. Other cases, you could talk about the 20th of July, because it's a recurring thing. Every 20th of July, you talk about the Apollo 11 lunar landing, because it's something that was really paradigm shifting for mankind. When we pick these events, we've been very careful to pick things that are genuinely paradigm shifting. You'd be amazed to see how many spacecraft launches or landings or space telescopes there are. There's more than 100 space telescopes. I mean, this in itself is just mind-boggling. And of course, you can't talk about all these things. It's obvious you have to talk about those that are the real big game changers, like the New Horizons. That's one of them, just one. And we have found about 200 or so of those, and have made a list, have described them in English with visuals as well, made them ready. Next step could then be to translate, etc. Another interesting case, this is a corner case, the Chelyabinsk I don't know where you were, but I remember exactly where I was that morning when I figured out that this thing was happening, and I was sitting there in front of YouTube and I was listening to the sonic boom, and it was just amazing. And I keep thinking back to that event because I bet you no planetariums did this event. Nobody. Maybe a week later or something when you realized, okay, this is actually pretty hot. And maybe you dragged in something from YouTube or however, but actually this has to be ready a few hours after. And the only way to do that is actually via blogs, because nobody would make a press release about it. So this is a corner case. So that's why we have the blogs also integrated in this. Other very obvious things, HST images, HST videos, no need to really lament on this. So when will this be ready? Actually, now. So it was released about 2 weeks ago on the latest Digistar 6 build from Evans and Sutherland, and I really want to emphasize the work that Evans and Sutherland have done. It's not that I'm paid here to say it, but they really went above and beyond the call of duty and rolled with this concept to integrate it. And I think it's very important to have someone as a front runner, because that's the only way we as a community can get together around a standard. It doesn't matter which standard, but we have to pick something and then work with that and make it something we use in our daily work. In less than 3 weeks, they will have a new build of Digistar 6, and that should have the rest of the things that I've mentioned here. The historical events, or the sky events we also have. These are things like conjunctions or anything going on in the sky, which is then described and has visuals with it. And the data so far included is those of ESO and Hubble, which was fairly easy for us, of course, since we have archives and we can make these JSON feeds very quickly. And then Robert Hertz's AstroPix project, they have an archive of a lot of other missions. And we hope also that SOFIA, the SOFIA mission, NOAO, NRAO, Subaru, and others can kind of join. You need a database, and you need to then deliver images and videos together in a JSON feed, which is kind of like an RSS feed, adhering to some standards which are described on Ben's new lovely website, data2dome.org. So it's all ready to roll. Let me show you, just as I finalize here, some screenshots of how it looks in Digistar 6. This is the portion of Digistar 6 which shows you the dome view. This is an image just ripped off the data-to-dome part, which is here. You have the standard cloud, the Digistar cloud, system resources. It says data-to-dome content, and then it says ESO, images, spherical all-sky images, and there you have an image. And you click it, and basically it then appears on the dome. If you don't know what you're looking at, you can kind of read through the text as you present it. This is not necessarily a news image. This is just an image, one of 20,000 images that are now included in Digistar from all these missions I mentioned before, and from ESO and from Hubble. Here is, I think it's a Chandra image from the AstroPix collection, and there is a logo and some metadata describing what you're looking at. And of course, in the future, there will be more and more of these things appearing in the software, because it is embedded in the metadata. Metadata, which are, by the way, on this astronomy visualization metadata standard that Robert and Ryan and I started many years ago, I think more than 10 years ago. So that is also alive and kicking. This is a slight augmentation of that standard. This is another image just randomly pulled out. And here is an overview. It's a bit hard to read, but this is how it looks. This is the browser window where you can basically just read off what it says if you're interested, or learn more information, or go to the website where the information is. And this is the cloud overview. So this is how the Digistar implementation has the clouds. You can connect them or disconnect them depending on what kind of content you have. And obviously, as there's more and more content, maybe you will choose to turn some of them off. It can also be a little bit too much, I imagine. So I'll leave you with the websites here, and thank you for your attention.
Were there any questions? Ryan, son.
Thank you, Carter-san. So recognizing that many press releases and compelling stories are going to include aspects that won't be the low-hanging fruit of images or videos. And so, for example, the TRAPPIST-1 announcement, it's great that Digistar is supporting this and that those users will get that content right away. How do you think we can address broadening that to other systems, at least until the time when Data to Dome can support things like orbital elements around other stars and more complex collections of data? So again, with TRAPPIST-1, we happen to be working with Robert Hurt on aspects of it. So we we received embargoed press releases, so we had access to the paper. We were able to create it in UniView prior to the announcement, and then released it immediately upon announcement. But how do you think we could address that longer term?
Good question.
I think there were many questions here, so let me see if I figured out which direction you take. You talked a little bit about the time aspect and about being ready, so being ready in advance. That's one aspect of it. The other one was about what about other systems than Digistar, which I think is a very important aspect. So maybe we can take these two and then work from there. So the standard is open, and on this nice website, data2dome.org, there's a very detailed table of the different tags that are possible to put in. It says very clearly which are mandatory. There are examples of how to make the feed. So any vendor essentially can go in and code to follow the standard in the feeds from the data providers, and then take the data and run with it. It is an effort, but it's not really a gigantic task to do.
Considering that the California Academy of Sciences does not have Digistar, but has UniView and has Skyscan, what sort of pressure as a major facility are you applying toward? Are you getting any satisfaction? You mentioned you put some of it into UniView yourselves.
So we actually had access to the texture maps for the NASA press release, NASA ESO press release before while the press release is embargoed. So we set up the entire system in UniView and immediately released that to the UniView community. We did not do the same for Digital Sky for various reasons. So I guess one thing that occurs to me to address the second question as you broke it out, Lars, is maybe we can figure out a way for at least major sources of data, of press releases like this, to sort of deputize certain institutions like Adler or the Academy or the Berlin Planetarium or wherever, to be able to make sure that there are quality assets created for the major planetarium systems in advance of a press release.
I just would very much like to get away from the whole manual thing in advance and be a little bit more like giving an advance access to anyone. But I'm not sure how we can do it, because at the moment the feeds are open, right? So you have to somehow make password protection or figure out a way to do it so that only those who are trusted can get access. And it's getting harder and harder, and this whole embargo concept is really getting very difficult to manage because people don't respect it and there's a lot of resistance, although it helps more than half of the journalists. We've done surveys, so that's something I think we have to look into and see if we can manage.
I just had a conceptual question sort of along the lines when you showed, a galaxy with a supernova. That's very nice. It's similar to what Doug showed with Worldwide Telescope. But then the question is, Worldwide Telescope, of course, being open is great. But it's a sense of, okay, what makes Worldwide Telescope so wonderful is you have basically layers of data sets at different scales. As Doug eloquently pointed out, many terabytes they have available, what AAS has available. So is there any work between, say, with your connection with Digistar, Evans and Sutherland, and Worldwide Telescope? Is there anything there regarding, so that you see contextually what that close-up is?
So
you have all this content,
yeah,
but you need kind
indeed,
of a continuum of data in and out.
So Digistar has a AVM support, and these images have AVM. Honestly, I've never seen the thing in function. I didn't make the screenshots. The ENS engineers made them, so it's only just been released. So I'm here talking about something I have absolutely no clue of. But I know that in ENS you can just click, and then, like Worldwide Telescope, you are there in context with the object on the dome in the same way as Worldwide Telescope. But something I never really managed to figure out is how to get content into Worldwide Telescope, because it seems it's all done on the client side. It's done on your side alone with the data. You can download on a one-to-one basis with the software and present. And I'm more sort of a proponent of the mass fabrication concept. But maybe Doug knows ways to get stuff into Worldwide Telescope to benefit the whole community.
Well, yeah, just one point about the way the data in Worldwide Telescope is managed. The AAS, or used to be Microsoft Research, supports this 15 terabytes of kind of core data, but actually the data can reside anywhere. Like I mentioned, the example where you do some processing. You get a layer file, and you can place that. Like I mentioned, you can process the panoramas or the all-sky surveys or whatever. Once you've done that, you can put that in your own private cloud. You can give that to AAS, and they can host it. You can, it's an aggregation of data anywhere. So there's no and actually one of the things that can be done is it's a great open source opportunity is to have tools like I mentioned the one image importer. When you do that, it's in the cloud, and there's the data is there, and if there were easier ways to take different types of data and put it in that format, like all skies and planetary surfaces, and if there were similar tools that were customized, then when people did that for themselves, it would be accessible for everybody. So I think part of this is to get the vendors to think about standards and ways of interchange of TOAST as a format, because the other thing about Worldwide Telescope is it's not. A lot of people think of it as an end-to-end system from servers to data to client, and ultimately, if all you wanted to do was the data and the servers, you could have Digistar be the client if it could render TOAST. So there's a lot of ways to interchange that, I think. But you have to start somewhere with a standard and see how that works and see how that fleshes out. But I hope that this moves in a direction for the vendors to see if there's interest and kind of value for themselves to be part of an interchange that allows for at least a subset of this sort of data, especially the stuff that has very currency because it's so valuable so early, to get into everybody's systems as quickly as possible.
Seems like things are coming together.
So this is not a question, but one thing I think a theme that's running through this morning with all the sessions is the idea that the planetarium is a visualization platform for all of the astronomical information, and you can never download that all. You need to have access to it. You have huge images in Worldwide Telescope that you're never going to download the whole thing, but you can pull what you need on the internet. So it's really important for a modern planetarium to be connected to the outside world. And if I can speak to the Japanese planetarium community, one big problem in Japan is many Japanese planetariums are not connected to the internet. And the future of the planetarium is going to be a network-connected planetarium.
That's many around the world, too.
and many around the world. So I think it's really important that we start to change that. So everything you can do, and Toshi's nodding, he's been trying very hard for years, is extremely important. And if you do sign up, I've got a Domecast this summer, which I'd like you to connect to. So.
Next up, we have Ryan, if they're to keep on schedule here. So, oh, good, HDMI, I guess. Plug right in. Great. So Ryan Wyatt, the director of the Morrison Planetarium, the California Academy of Sciences, former colleague from New York. So have at it, Ryan. Great. So welcome Ryan Wyatt. Thank you.
So I'm going to do one thing before I start. So I would like to a little bit from discussing the data, with the kind of underlying content that we want to bring to our audiences, to talking about the mechanism by which we try to do that. And namely, because I'm a strong proponent of not just beautifully rendered shows in our planetariums, but also live content presented in domes. I'd like to bring up the topic of professional development for how we empower planetarians, people who work in planetariums, to communicate current science. And I hope you'll indulge me, because I'm simply going to use my institution as kind of a case study for how we do this, and ask some questions about how we might expand that model to the community at large. So this is a little bit of a dated image of my team, but it's a combination. About a third of the people in this image are content creators who make the planetarium shows that we run at our facility. And about 2/3 are mostly part-time, but are presenters, people who are actually in front of an audience talking about the science on a daily basis. That may be in the planetarium, it may be at other venues, but I believe that we have a successful model for an institution to be able to talk about contemporary current science, and I'm hoping that some of the lessons that we have learned can apply to the community at large. So to give a little context, and this is here also to remind me not to just mention that this topic goes beyond astronomy. The California Academy of Sciences is an institution that has existed for more than 165 years. It is a research institution, but we have a new building in San Francisco's Golden Gate Park, the largest green building in the world open to the public. Our core mission is not communicating astronomy. Rather, astronomy is one of many science disciplines communicated at the institution, and indeed in the planetarium. We create shows about ecosystems, about earthquakes. Our upcoming show is about coral reefs. And so as we think about data, and this is an image settling down onto the roof of the Academy, the living roof, the hill in the distance across the glass piazza is what conceals the planetarium dome. So as we think about data that we want to highlight in our domes, I hope that we will think beyond the universe and also think about planet Earth as we look at the urgency with which we must address terrestrial issues in the coming years. We really must not forget that the data aspect of what we're talking about must extend to Earth-oriented data as well. It's part of my missions institution, but I hope it's part of everyone's mission to bring that message to larger audiences. That said, I will focus basically on astronomy in this presentation. So again, that dome in the distance conceals the planetarium. If you were to go inside, you would see a 290-seat theater with a 75-foot 23-meter diameter dome, and it's tilted at 30 degrees, much like a IMAX dome theater. We present typical shows in here about astronomy, as I said, also about earth sciences, but every show has a person, a presenter, speaking for at least part of the program. And one reason I wanted to bring this topic up of professional development as well is that 17 years ago, Carter would bring people into Hayden Planetarium's dome, let the Zeiss remain covered for the duration of what could sometimes turn into several hours, late in the evening, covering it with carpets and pillows. People could lay in the middle of the theater and go on a tour of the universe. That was 17 years ago. Over a period of years, after I joined in collaboration with Carter, Brian Abbott, we tried to proselytize, we tried to expand that message about live presentation, about the three-dimensional nature of the universe. Not even at that point the changing nature of our knowledge about the universe, although that was implicit in some of the presentations we did, but just to talk about the three-dimensional universe. And that was a paradigm shift for planetarians who are accustomed to talking about the night sky and effectively an earthbound perspective. It took, and only now am I feeling like, and well, I should say, it only took a few years for the planetarium software to catch up. Certainly within a decade, many planetarium software packages supported three-dimensional data. Many of them used the AMNH data set. Power existed in planetarium domes around the world to talk about this, to take people on a tour of the universe. But it was certainly more than a decade before it was happening with regularity, and it's only recently that I've seen people taking advantage of the capacity of the software to do what started at AMNH 17 years ago. So now, as we look at these further paradigm shifts, talking about contemporary current science, about bringing new data into the dome, and about the massive data sets from LSST, from the Dark Energy Survey, from these, again, paradigm shifting scientific instruments, we still have to now build on this momentum and look at how we can bring along the people who work in these places, in these domes, to be able to talk about the spectacular discoveries. So that's why I opted for this topic as my few minutes in front of the audience today. As I said, every planetarium show includes a live presentation. This is Mary, one of our presenters, showing off our vintage planetarium pointer. The show might be entirely digital, but we still have that beautiful analog pointer. The typical show will have a 20-minute, 25-minute pre-recorded digital presentation, but a presenter will speak for 5 to 7 minutes of that in the middle of the show. They will introduce themselves at the beginning. Often that live portion is dedicated to talking about new results, about recent news. So maybe not on the rapid time scale that Lars discussed, but still very recent discoveries that relate to the topic of the show. And finally, our presenters wrap up at the end of the show and are available for questions afterward. In addition to shows that are partially pre-rendered and partially real-time, our presenters do a fully real-time tour of the universe as the last show of every day. So this is our presenter Josh, silhouetted against our monochromatic cosmic microwave background, eliminating the color confusion that could result from common depictions of it. That's a story for another day. But these fully live presentations also include a monthly universe update program that typically I deliver, where along the pathway of a tour of the universe that starts at Earth, goes out to the CMB and comes home, I'll just talk about, kind of riff on the last month of current astronomical discoveries. So we build UniView modules and we do pretty much work entirely in UniView these days, to allow us to talk about this current science. And then we do, as I'll mention later, share that out. I'm not the only one who presents those kinds of shows, however. We have a Thursday night program, which is our Cocktails in Science program. So every week, we're doing a live program or 2 or 4 in the planetarium. And our presenters work on that, work on those programs, and they do it collaboratively. And that's the first lesson that I think is worth mentioning. So if you go to our shared Google Doc folder, and Mary will have to forgive me, this is her script for her live section of our current show incoming. Each one of our presenters works on a shared Google Doc. They hash out arguments about how to talk about certain things. This can happen very rapidly in the case of a current event, or it may happen over a period of months if we're developing a show that will go on for a while. So the italicized line there is the pre-recorded line that then leads into the live, unpre-recorded, the real-time segment of the show. And this is the script, which everyone agrees on in sort of bullet point format, written in Mary's words. And she can improvise from this. She has total control over that. But this is a shared process. So we typically have 6 to 8 people working on this script under the supervision of myself and our assistant director. So that's for that live section that is placed in the midst of our show. And then our technicians are also looking at this to suggest images and to talk about the process of supporting these ideas with data and imagery. Just as another example, this is my document for the Universe Update last month, and basically just listing out stories. Anyone who has access to this shared folder can comment, offer suggestions. So it's a way for us to collaborate, share ideas, and also sort of cross-check each other's information, introduce people to new ideas, and basically sort of collaboratively work in these projects. Before I talk about our other venues, I'll just mention one other thing that happens in the Planetarium Dome, and that is our Dean Lecture Series, our Astronomy Lecture Series. Unfortunately, this is the only image I have of a co-presentation by Joel Premack and Nancy Abrams. And it's just got a PowerPoint slide up on top, so that doesn't really illustrate my point. But we typically work with our monthly astronomy lecturer to create assets, 3-dimensional data, or flight paths that will illustrate concepts they want to talk about. So typically the way we do it is they send us their PowerPoint a few months in advance. We hash out what they want to talk about. We suggest content that they might want to use. And that's another way that we both fuel some ideas for our presenters to talk about in their segments or in their live shows, and also to create data that we then share with the community at large. Briefly, I'll just note that we have other digital spaces in which the presenters present. One of those is the queuing area for the planetarium. So we have a high-resolution video display on one wall of that space. So 10 minutes after the planetarium show starts, we bring people into that space and have a more intimate discussion about typically astronomical content. We also have a 3D theater. We can play films, but we often do real-time content in there, hosted by a presenter. And we also have a space that's used most frequently for our kind of breaking news, current science, that is on our floor. And here, actually, we have a picture of Josh talking about the TRAPPIST-1 discovery the day of the press release. And he has an interactive model in UniView up on the screen, so he's able to fly people to the individual planets, have conversations about the discovery, and that's something that we did for the few days after the press release. So this is more of an ad hoc opportunity. And again, collaboration is an important part of this. So we have some presenters, well, the presenter who took the picture is sitting in to learn more about this. We're having conversations around it, and we're interacting around how to communicate this content. So those are all venues within the Academy: the planetarium, the queuing space, the 3D theater, and then this small, intimate digital environment, the exhibit space. We have also recently, in a focus on current events, set up what I call our Universe Update webpage. These are stories that are written by the presenters and videos that we produce, often based on the Dean lectures, the astronomy lectures that I mentioned before. We'll record the lecture for about 5 or 15 minutes before they deliver their talk, and then edit in HD versions of the visualizations that we've created to support their talk. So an example of that is for the astronomer Franck Marchi, who talked about asteroid moons. And this, by the way, crosses over into an interesting territory of the astronomical artwork versus data visualization. We can come back to later. But we created a series of models. I'll show you a version in the dome tomorrow. But we created a series of models of the asteroids with moons that Frank had discovered over a period of several years. So we cut that into about a 2.5-minute video, and that's something that we're doing for all of our Dean lectures. The script for that, the interview is done by the presenters. They get to interact with the speaker before, during, and after the talk. And then the final edit is done as a collaborative process as well. And then finally, we just introduced our own planetarium Facebook page. This, once again, is moderated and supported by the whole presenter team. So it's a chance for them to share out news stories as soon as they happen. And it's a way of complementing the Academy's not so astronomy-oriented main Facebook page, which has 1 million followers and is so tightly controlled that they don't want to basically have any post on their Facebook page that would in any way diminish their overall popularity. So they've allowed other channels to exist within the Academy, so we are creating an astronomy-focused channel. So all of those are kind of collaborative ways that we allow our presenters to participate in creating content, and often very much focused on current events in astronomy. And then finally, I'll just notice one other thing that we do. In addition to the lecture series and interacting with astronomers, we also try to host workshops, in this case a UniView workshop, so that our presenters and our programmers can work in a shared environment talking about the underlying software. So I want to take a few lessons from this before I try to think about how those might apply to the broader community. So the way that we've tried to build presenter capacity at the Academy is very much based on collaborative program development, and that's creating member shows, adult programs, also those web articles and Facebook posts, creating the content that appears in the dome and outside the dome. And then it's also applying this related knowledge across platforms. And I think that's also very powerful, that you can get into a very, particularly with the planetarium demanding a very specific sort of abbreviated way of talking about things for a short live segment, versus how you might talk about that in a lengthier live show, versus how you might write about it for a Facebook post or write about it for a more extended article. These different channels allow the presenters to really work in different modalities, and it reinforces the content, I think, in a very strong way. And finally, we try to provide professional development opportunities in the form of lectures, participating in conference calls. In the US, we have NASA's Museum Alliance, which supports many conference calls where people can call in and again, interact with a researcher working on a specific topic, as well as these meetings and workshops. So that's the focus on the presenters. Before I try to broaden that, I do want to just mention the content, sort of a few things that we've learned by putting content out into at least mostly the UniView SCIS ecosystem. So stepping back from the professional development for a moment and focusing more on back to the kind of data topic. We've already heard about Data to Dome, which is a great initiative to look at how to push content out to planetariums. Of course, we've already heard about VAMP, or about the astronomy visualization metadata as well, which is a subset of something called VAMP. which, as Lars said, we started more than a decade ago. Those are part of the kind of infrastructure for getting these that exists to capitalize us to get flat images and relatively straightforward content out to our planetarium colleagues. However, we do find that the complexities of a lot of what we want to talk about, as I kind of hinted at in my question to Lars, requires intimate knowledge of the workings of the individual software platforms. When we talk about putting orbital trajectories in for spacecraft, or the orbits of planets around, exoplanets around another star. And so, as any content that we've created, we have made available through the SCIS community content sharing site. But I think what's interesting about this, and I think the challenge for the community, is we should think about ways that are more kind of cross-platform for sharing this. So typically, Digistar users put their Digistar content into a nice kind of locked Digistar safe. The UniView has their individual UniView section. Digital Sky users, RSA Cosmos's Sky Explorer users, and these individual silos don't have an opportunity for sharing between them. And quite honestly, for us, because UniView is our core platform, we often don't take the time to translate that to Digital Sky, just because it's added labor that's not going to give us any payoff other than the warm feeling of sharing content with our colleagues. So it would be to think about, just as an abstract notion, some way of sharing content in a way that's not isolated to these individual platforms. And I could imagine a site where if we could just, the question of course being where to host it, you could just put data on a site that's open access across platforms, and if you're a Digistar user and you see a cool UniView package of content and you just want to pull that across, try to tease out how to make that work on Digistar, and then the requirement being that you need to put it back into the repository, share it back out in some sort of abstracted Creative Commons way, back to the community when you've made a viable Digistar product from it. It would be great if something like that existed. I know there are a lot of barriers to that, but it would be great to think about how to make that work. But that led us to think a little bit about what a meaningful sort of bundle of assets looks like. And this is very much building on the same kind of conceptual framework that Lars talked about with Data to Dome, and the conceptual framework actually behind AVM. As we talked about it internally, and this is really coming from, for those of you who know him, Dan Tell, that something to be really meaningful to be able to take as a presenter, to take it from another theater and implement it on your own, it really needs to include kind of the following. You need the relevant scientific data sets, of course, as well as making sure you have all of the shared kind of basic data sets for simulating, the phenomenon and its environment. You really need appropriate reference material, which means a human readable script or reference audio. The press release would be the corresponding part of like the AVM standard and the JSON feed. And then just very practically, if you're sharing this out to a wide audience who are not necessarily very technically oriented, you need, and again, thinking of this in terms that are fairly focused on individual platforms, a simple control interface so they can interact with it. So as we thought about it, that's kind of those are the necessary ingredients for something that we want to share with another theater. But going back now to kind of close out just the idea of how we extend what I was saying seems to be a successful model of the California Academy of Sciences for the professional development of the presenter team that's in the theater on a daily basis, or in these multiple venues on a daily basis, communicating astronomy content. I really think that collaborative program development is a key component of why we do as well as we do with our presenters. I don't know how we do that, how we scale that up to our community at large, but it would be great to think about how we can create a community of DOME users who are not only bringing data into the dome, but are sharing knowledge and experience around how to communicate about it. And it would be fantastic if this could also be a truly international and cross-platform collaboration. I think we see this with the Digital Sky user group in certain ways, the UniView user group in certain ways, the Digistar user group in certain ways, but to really think about this as more of a fully community-oriented endeavor to be able to talk about how we talk about science would be fantastic. And then in the professional development, I think we have a clearer route forward working with the Vision 2020 professional development efforts. I am on that team as well as Kumura-san over there. We have both worked with Carrie Berglund from Illuminati to talk about what our community could use in terms of professional development. And sort of the key takeaways that we had in the initial phase, and this is distilling a lot of work, unfortunately, but is to create online resources that can support planetarians in various endeavors, and then also to piggyback workshops on existing conferences. One thing that became clear is that planetarians didn't want to really go to a separate event. They wanted to think about how they could spend a half day or a day before or after another conference or workshop and extend their capacity. And then I think also to look at these networked opportunities offered by OpenSpace or other software platforms and think about how we could leverage those for fostering communication between educators and scientists. So maybe before we do a public event, we have a kind of topical training for planetarians to interface with the scientists to get, much like the Google Hangout that Carter showed, with different people learning from the scientist how to talk about a specific topic. So those are just a few thoughts on how we can try to expand this to the community at large. But quite frankly, I really just wanted to get the idea out there to really foster some discussion around this, to think about how we can learn to communicate better as a community about these emerging complex topics. And I will just mention in closing that we are going to have a Data to Dome session at LIPS in 2017. For those of you who don't know, LIPS is the Live Interactive Planetarium Symposium, a sort of small ragtag group of presenters who've gathered to share their knowledge around communicating effectively in domes and have been doing this for several years. And we are looking forward to presenting. I think both Mark Subarow and I are signed up to talk in some appropriate format at their meeting this summer at Ball State University in lovely Muncie, Indiana. So,
home of Close Encounters.
Exactly. Yes.
Good movie.
All right. So, thank you very much.
That was great, Ryan. Thank you. Are there any questions?
Yeah, great talk. I think it's a really important topic that needs to kind of be on top of our minds as we go forward. A couple things that occurred to me. One is when I went to Fort Worth, one of the things that I did was I wanted to get this professional development to my presenters, and I actually had a great educator that was plugged into this thing called NISENet. Do you know about that network? And there's a lot of great professional development opportunities there, and which are just immediately. I mean, a lot of this professional development. Sometimes we think of it too astronomy specifically, and I think this is all science communication, and there are other people that have more resources than we do that have created excellent professional development, and nanosciences did this, and it's very applicable, and we went our training through that, and it was really excellent.
Yeah, that's a very good point.
Yes. And the other question is, I'm trying to figure out, because this idea of sharing is fantastic, and I think it has to happen, but like in the warm, fuzzy kumbaya thing, I imagine that, like what I'd like to see happen is where if the burden of creating like what I call science shorts or daily science updates or whatever you want to call them, if that were shared, and let's just say every planetarium did one a week, you'd have a huge library that any one planetarium wouldn't have to curate or create them, and we could all gain from them. But is that too ambitious? But I know people like Dan Tell is incredibly prolific, and he's also really helpful. We have some people in Worldwide Telescope that have been taking the models he's used, and there's kind of one-to-one relationships. But do you think it's going to work to make it a network where everybody contributes and has this kind of, again, contributes in and pulls back out in some way? Or do you think there are going to be these centers that have, because of professional development or training or expertise, are going to be the places where this originates and then it gets pushed out from there?
Or just because of sheer number and resources, I think, is part of it, that there are probably a smaller number of facilities that have the number of person hours to the human capital to be able to do that work. And so I think if we could find a handful or more than a handful of facilities that had different software platforms or had different links into different software, that could be an interesting model to explore, but I'm making that up as I go along.
Toshi, did you have a comment?
I agree with you that sharing the data bundle asset to the cross-platform is great if it can. And I think that there are some technical or political issue, but anyway, it's a great way. But from more basic viewpoint, I think having lots of recorded video or something to teach about how to use a data set is more common and useful for many planetariums or museum of people, because of course data set is important and must have, but more important is how to use the data set or know what could be done in the daily planetarium lectures or shows. Because you're professional side, okay, you know the latest science topics, but it's also difficult for the more common planetarium people or museum to understand what we could have, or in other platform what they have. So just in simple, just a recording movie on the any platform like Uniview or Worldwide Telescope, Open Space, anything is okay. Just showing the actual example of using the data set and how to tell the story of that related on the usual daily show is more important, and it's a good start point for the beginning.
Yes, certainly agree it's an important starting point and a good way to open up the doors. I certainly hope that we will move to a broader range of live presentation.
Yeah, I think that's a really good point. Yeah.
Just picking up on that point about the live presentation, I would really like to reinforce the notion that the Live Interactive Planetarium Symposium LIPS is a really fundamentally important movement because it deals beyond the question of the technical issues of learning about data transfer and so forth. It really deals with live presenting as a professional development situation. It deals with best practices, do's and don'ts. It's a very practical thing, but it really is. It really gets down to the nuts and bolts of presenting live, and you get a bunch of really enthusiastic. It goes beyond ragtag. They're really an enthusiastic bunch of people who are very committed to using best practices in terms of getting ideas across to the general public.
I should say ragtag in the sense of like educational guerrilla warriors who are out there to really change the way we're doing things.
Lars?
Yes, so I found this really thought-provoking in many ways. I liked the whole point you made about co-owning and about using that as motivation, even in a place as well-funded as yours, you know, that there are issues there that need to be looked at. So that was an eye-opener. doing these bundles between planetarium systems, I'm sorry, but that's just not going to happen. At least not in this decade. But maybe if someone pulls out the big wallet and starts, making it a business incentive for the vendors to actually share at that level and put in the resources, maybe in the next decade that could be possible. But still, we're making the small steps. My point was maybe more addressed to Mark in the next, IPS leadership era. I think IPS could play a little bit more of a role as an informer, because I've heard people here talk about doing dome casting and doing all sorts of things, and I have absolutely no clue this is going on. And that can't be right. I mean, simply that should be something that we know about on, for instance, the mailing list that I actually enjoy reading, but it's very rare between the information that's worthwhile noting. But seeing the big flagship institutions as yours doing these important things is really, I think it's very important, because it gives us the hope that we can actually collaborate and piggyback on each other's shoulders. So more of that, and let's get the information out there instead of bitching about slideshow scanners or whatever they're talking about. Sorry.
Well, I just want to, because I vehemently disagree with your first point, which is to say that I don't think it's going to be less, it's not going to be more than a decade to be able to, to automate the process of exchanging bundles, yeah, that's a pain. But to work with a group of enthusiasts to be able to say, hey, here's what it looks like in Uniview, here are textures for these planets. The TRAPPIST one is a perfect example.
Of course.
It's low-hanging fruit in the sense that a few institutions could leverage this for the community at large, because there really are fundamentally only 7 or 8 planetarium software platforms that are 99% of the planetariums that are out there.
But clearly, I also didn't mean that. And in fact, I don't know why those textures were not just attached to the Spitzer press release, because then they would be in AstroPix already, and thereby already in the domes who adhere to this data to dome standard. So I think we're on the right track when it comes to this low-hanging fruit. I was talking about the more advanced show sequences and stuff.
Well, there are a lot of subtleties around the textures as well. One of the reasons that we had access to the textures early is because Robert wasn't sure what we needed to work in Uniview to be able to create something that, for all the specular reflection, the cloud, like how to separate it all out in a way that was meaningful for us. I assume that's different for Digital Sky, for Digistar. So we're going to have to, there's still work to be done to be able to supply the correct stuff, because I think it's non-trivial. But I still think that we can make a lot of headway with a relatively small investment in terms of number of person hours.
One comment about having group networked events. Our public programs at the American Museum of Natural History said, and consistently said over the years, we're New York City. Why should we have a program to listen to somebody else from somewhere else when we can invite them to the Hayden Planetarium? And very successfully, Mark and your team in Chicago had Michael Turner, thank you, our keynote speaker at IPS in 2012. Michael Turner, cosmologist, speak, and we had 15 planetariums. And thanks to Mark's incredible help with each one of those facilities, making sure it worked. And so we sold out. And people came to the Hayden Planetarium to see someone who was not at the Hayden Planetarium. And when I bring this up and say that was great, the public programs people say, well, we don't think the people actually knew that he wasn't coming. So there's institutional momentums at certain places, not the least of which New York. But really, I think we should move on. But the really good discussion. Thank you. Thank you.
So if I could just close, let me comment on Lars's question about IPS and awareness. So IPS will be much more involved in connecting the planetarium community across platforms. That's the purpose of this workshop, which is not something we've done before. And just so everyone knows, it's not just all you people in this room in this workshop now. There are people watching all over the world. I'm getting emails. So in the last half hour, I've got emails from Argentina and Mexico and Greece and Canada of people who are watching and enjoying what they're hearing today. So there'll be a lot more of this, for sure. And thank you all who are listening online. We're going to have a break now and enter our practicum session. But if you have a chance, hopefully you can join us in our morning or whatever time it is for you tomorrow.
And we're 1 minute into our practicum work. Thank you all.
You know what? If people need to go to the bathroom, you can go to the bathroom.